O evento está sendo transmitido ao vivo e gravado pelo YouTube. Ao permanecer no local, o participante declara estar ciente e de acordo com a captação e utilização de sua imagem e voz na transmissão e na gravação do evento. This event is being broadcast live and recorded on YouTube. By remaining in this venue, participants acknowledge and agree to the capture and use of their image and voice in the broadcast and recording of this event. Okay, so it's a great pleasure for us to have here Professor Raghavan from University of Illinois Chicago, from their Math, Statistics, and Computer Science Department. Professor Raghavan will give his mini course in algorithms for stochastic games, structured stochastic games. And it's a great pleasure to have you here in Brazil, in São Paulo, Professor Raghavan. So this is the first of his lectures for this mini course. And please, Professor Raghavan, the floor is yours.
Dear students and professors, this is my third visit to Sao Paulo. First time in 2002 I came, and then in 2014 also I came. But that doesn't mean anything. I don't know the local language. I can speak only in English. I wish I knew the local language so that I can communicate better. How do I try? To give an idea, yeah, okay. Okay, yeah, okay. To give an idea about stochastic game, one must understand something simpler, what are called Markovian decision process. How can you help me? Because I don't know the way it works here. Next slide. Yeah, okay.
It was there.
Okay. Now, very recently, I start with a simple example. In India, to select a student for medical college, they have to take an annual exam conducted by the Government of India. Now, when you take the exam, it is offered only once a year. Say, assume it is January 1st. The students who take the exam are evaluated, and then their scores are already announced. But sometimes what happens is you have intelligent students and poor students, rich students, all kinds of students are taking that exam. So sometimes a rich student may find it convenient to somehow get a leaked out question paper. In the past, many times the question paper has been leaking out. So you have that information. So the students were complaining, a good student, whenever the question paper leaks out, you have to take the exam again within 6 months, a particular day. So the issue is, a student who has done very well, why should that student be penalized for taking a second exam? So they complained, and then there is a big strike which was going on. Even the Prime Minister of the country is struggling. But I think of this as an example of a Markovian decision process. So what is the process? The students should be given the benefit of doubt. How do you give the benefit of doubt? So the student, when the student score comes, either the student can retain that score, or in case he decides to take the exam again, in the middle he may say, I don't want to take the middle exam. I think my score is good enough. Or if I take the middle exam, then the student should be allowed to keep the better of the two scores. And then suppose he thinks he may even make it worse because he has struggled hard, then best thing is he can keep the first exam score. But if there was no leaking out, still they can take the exam again, but only next year. So next year's score is discounted. So this is the kind of model which one can use to see what can be done. So that is the simple model of a Markovian decision process. So you have a system with n states. S is 1 to n. And in each state, in the exam, you think of the exam as January 1st exam. If the game leaked out, question paper leaked out, it's in between the second state, etc. So the states are moving from 1 to n. And in each state, you have a certain number of actions. And you have some reward in each state choosing an action. Then once you have collected the reward, the system moves to a new state, which will depend only on your current state and current action. It doesn't depend on anything else. So that is why it is called Markovian. Now, you have two kinds of horizons. One is a finite horizon. You may take for a few years. See, you may observe for a few years, continue for a fixed duration, and accumulate the immediate rewards. Or infinite horizon, you play non-stop, but all future rewards are discounted at a fixed discount rate. Now, the decision maker has various possibilities of choosing actions. So, a policy for a decision maker is to choose an action which is called Markov if it depends on the day and the state of the day. If I am on the 10th day, what action I take can depend on the date, but not on anything else, the current state and the current date. With this, that's called a Markov policy. A policy is called a stationary. Whenever you come back to the same state, you take with the same probability the actions. That's called stationary. A more complicated policy is a behavioral. They depend on each day on the entire past history. That can be very complicated. And a policy is called pure stationary. Whenever you reach the state, I do the same way. I don't change it. See, if I come to a state, I choose the same action. This is pure stationary. The interesting thing is, To play this kind of Markov indecision, it is enough to play pure stationary. I start with a simple example. The system has two states. It has two states. In state 1, if the player chooses the first action, he gets 5 units, $5 or whatever it is. If he chooses the second action, he will lose 4. If he chooses the first action, he will get 5. If he chooses the second action, he will lose 4. Then, depending on the action chosen, the system moves to a new state. Namely, there are only 2 states. So it moves to first state with chance 0.6 and the second state with chance 0.4. If it chooses the second action, it moves to the first state with chance 0.1 and to the second state with chance 0.9. Now in state 2, you have 3 actions. If he chooses the first action, he will get 9 and move to state 1 again with chance 0.9 and chance 0.1. If he chooses the second action, he gets nothing and he remains in the same state with chance 0.9 and move to the first state with chance 0.1. Like that. If he chooses the last action, he remains in the same state. All these things, it's okay. Then I can compute what is the expected immediate reward on a particular date when you start the system on day 1 and use a certain policy pi, and you can compute those expressions. These are purely calculation. So the first important theorem is there is no need in playing such games to go beyond Markov policy. That is enough. It is enough to play Markov policy. This is the first theorem. And what is the intuition behind it? One may wonder how this is possible. The key is mathematical induction. Okay? Suppose a good student writing an exam is working out the full details of which question to answer first and what next, etc., with careful details out of his detailed memory. This is how I should answer the question paper, given the fixed time. A bad student who is looking at him, who can be copying him, can do without any memory. All he has to do is, outcomes are the same in terms of their solutions. They both would have gotten the same solution, while the second guy never actually did anything. He only copied. Okay? The last one is my personal experience. The bad student may even be getting better grades for the same solutions. See, as a student, I was asked to write about Shakespearean tragedies. I had memorized a certain beautiful sentence. I wrote that sentence, and my friend who was sitting next to me, he says, "T, your sentences are sound. Can I also use that?" He asked me. Said, "Go ahead." There was only one difference. In mine, it was full of spelling mistakes because I have only memorized the words, but I could never spell properly. He knew the correct spelling and he scored above, and my teacher punished me, saying, "You better words 10 times, 10 times, 10 times." That's what it is. Okay. Now there are 3 main theorems which are key to computing. Suppose you start with a Markov policy. You start with a Markov policy, and for the first day, you want to change it. So you change to an arbitrary policy, F. So originally you had a plan to use a certain Markov policy, and instead of that, suppose for the first day I use a different policy and switch over to the Markov policy from day 2 onwards. If I cannot, by doing this, improve the Markov policy, improve means, so the Markov policy pi star is better than any such policy where you do something for day 1 and switch over to the Markov policy again. For any one of them, if they cannot improve, then what you have is the best policy. The second one, you may start with a Markov policy and you may say, let me see whether I can improve it. I use a different policy for first day and I see an improvement in some state. Then the best thing is simply to scrap the original policy and switch over to this new policy. And this is the second major assertion. The third major assertion is, for any beta discounted Markov decision process, for all beta sufficiently close to 1, you have the value of the Markov decision process is a rational function of beta, and there exists some beta naught beyond which the same pure stationary is optimal for all such processes. And based on just these three non-trivial theorems by David Blackwell, we can do something called a policy improvement algorithm. So, what is policy improvement algorithm? You start with any action on day 1 in state S. So you collect immediately RSA, that is your immediate reward. Then you move to a new state S prime with chance Markovian transition P S prime given S and A. And then once you move to the new state, you switch over to the original policy which you had in mind, F infinity. Then you know how much you can expect there. So if this can be improved at some state, if this set is non-empty, there should be some state where it can improve, then you scrap the current policy and use the new policy. How do I explain that? I am a person who is renting a machine in a shop. And the machine can be in 4 different states. If it is an excellent machine, I want to rent it for $100. If it is a good machine, I want to say it's a good machine, it will work, and I charge you only $80. It's a fair machine, I charge you only $50. It's a bad machine, I charge $10. It might work or it might flunk. Okay? You have the option to take any one of the machines. But if the bad machine flunks, then it is my responsibility to replace it with a new machine. The new machine costs $200. New machine costs $200. Okay. So let us take the policy of the transition matrix. Suppose I say I don't want to, when I sell the machine, whatever is the machine, I say, don't change, don't change. Don't change if it is a good machine, excellent machine. Don't change if it is a good machine. Don't change if it is a average machine. Don't change even if it is a bad machine. D means don't change the machine. C means change the machine. Or buy a new machine. Okay, and beta is 0.9. And when you take the transition matrix from state to state, with rows and columns ordered by row 1 is E, row 2 is G, row 3 is F, row 4 is B. So you move with a good machine, excellent machine, may remain an excellent machine with 70% chance next time for the next rental. Or it can be a good machine with chance 0.3. It's either excellent, it slowly deteriorates. The machine deteriorates to the next stage. So 0.7 and 0.3. So if you started with a good machine, it will be good with 70% of the time, and it becomes fair with 30% of the time. If it is an average machine, then 60-40. But if it is a bad machine, for sure it is going to go and fail with 100% chance. So what you do is, whether I should stick to DDCC or should I stick to DD instead of C, a D, which is an adjacent policy. Okay. For an improvement by testing an adjacent policy, and this is the test procedure. This is the test procedure. Okay. And once you find, if by, just a minute, instead of DDCC, I choose DDDC. Let's see what happens. And you don't spend the time computing everything, only some calculations are made. The whole problem is, you can spend the time calculating the entire thing at the new level, or just calculate a small portion. And that's the whole idea of policy transition. That is the policy improvement. So the QB, this adjacent policy DDDC, and then when I evaluate it, you start with suppose you start with an average machine. That's what, let me call it, I don't know what the name I gave, just a minute. A fair machine. Suppose you started with a fair machine and sold it for, rented for 50. And then, that is on the first day you collected that. And still the machine is, with 60% time, it is in a fair machine again. And 40% time, it is becoming poorer. Okay? So, you calculate this 50 plus a discount factor of 0.9 times that. If it is better than what you had previously, by changing it, then what you do is, you permanently change it and then compute the new thing. And this is what is called policy improvement. But there are only, in this case, either D or C in each state. So there are 16 to power 4. There are only 16 pure stationary strategies. So you move from one stationary strategy to something which is better. But you don't go through all the 16 to come to the answer. Within a few rounds, you will be over. So you will save a lot of time calculating that. Now the second one, I explain in terms of my examination in India. Suppose, you see, there is something called an LSAT examination here for law degree, to enter law degree. So you have an LSAT score, which is something. But you can take LSAT again. If you take a second round, the examiners treat your score not as the first score, but not also as the second score, but the average of the two. Average of the two. Suppose you took this several times, say 10 days, 10 times, 10 years. So your LSAT score is the average of all of them. That's how they treat you. And they have a cutoff. So if you are above this cutoff, you have a chance to get into law school. So some law schools can accept even cheaper people. They collect more money and then enter you. That's what happens. Then we come to, you think of it like, instead of discounting, you can take a Cicero payoff. This is what is called the Cicero payoff. And this, for any stochastic matrix P, this Cicero payoff always exists, which is called Q. Q is the limit of the Cicero limit of the Markovian matrix P. And the P has several properties. P times Q is Q, Q times P is Q, P square times Q is Q, everything is Q. Okay? Then we come to the very important theorem. I wish I could, no, if I have to explain, see, the problem is, it is, each mathematical step is a long process. You can only give the flavor of it in a workshop. That is the problem. Okay. The matrix, given any stochastic matrix P and its Cicero limit Q, the matrix I minus P plus Q is always non-singular. And what is its inverse? It is something. But interestingly, it is also the limit of beta increasing to 1 of the discounted beta power t p minus q whole power t. And if I subtract q from this one, that will be the last one. We have 3 assertions. These are deep assertions due to Blackwell. These are not. First assertion is quite easy to prove. But the second assertion and the third assertion depends on, just a minute, something called the theorem of Zygmunt in Cicero limits, etc. The Zygmunt's theorem was invented in the last century. And somehow it was purely a theorem of mathematics, but Blackwell was the first person to effectively use it. Okay, just a minute. Let's take this. Let us first state suppose you are given a bounded sequence of reals, and beta is a number between 0 and 1, strictly less than 1. Then lim_inf of 1 over n plus 1, summation at 0 to n, because at is a bounded sequence, this lim_inf exists. Similarly, lim_sup also exists. this left side exists, the right side, rightmost also exists. And it is the things in between are also, they are also existing. There's no problem. So Zygmunt's theorem says this is all the thing which Zygmunt's theorem says. Follow me? So you have a lim in terms of averages, lim chup in terms of averages. This one, the lim inf and lim chup in terms of discounting. The lim inf and lim chup of discounting are caught between the lim inf and lim chup of averages. If these two, the two extremes collapse, the middle two also must collapse to the same thing. That is common sense. Okay? So Zygmunt's theorem states only this one, nothing more. But then there were famous mathematicians, just a minute, Hardy and Littlewood. They came with the important statement that if the middle two things collapse, suppose I know lim inf of this and lim sup of this are same. If these two are same, why should these two be same? The two extremes need not be same, even though the two insides can be same. The Hardy-Littlewood remarkable theorem is, if the middle two things collapse, even these must collapse to the same thing. You follow me? That's what he said. So if a bounded sequence is above summable, the middle two things, then it is Cicero summable, the two right things. So Blackwell resolves this by not fixing beta. So if you write down the worth of the policy, pi, using beta, and u beta the expected total return, then pi is optimal if b beta pi is u beta for all beta close to 1. See, there may be a policy which is the same no matter what beta you use beyond a certain number. For all such betas, you still use the same policy as the best policy. If it exists, then it is called an optimal, uniformly optimal policy. Something which can be close to it for all beta, but as beta goes to 1, these two may come to the same limit. This is what is called a one-optimal policy. Now, based on these two things, the first important theorem is, suppose you start with a pure stationary policy F, and the immediate reward is RF. The expected immediate reward is RF, which is a vector which depends on the state. And then with the discount factor beta, you are going to collect the new result. Suppose you play the game only 2 days. The policymaker is allowed to choose a policy on day 1 and then collect whatever is this expected income, which is RF. But then once it moves to the new state, depending on the state you reach, a fixed amount W of S at state S is given. You follow me? So you, instead of playing the infinite one, what you do is you play the 2 days. First day, you receive an expected reward RF. Second day, a fixed amount W, depending on which state you reach. Okay? And then if you evaluate this expression, the operator is both monotonic and a contraction. It's an operator which is both monotonic and a contraction. And once you know it is a contraction, it has a unique value. The operator has a unique fixed point by fixed point theorem, okay, Banach contraction mapping theorem. And because of that, you can now say that the Tu of S for any u, any vector u, is the maximum of A over RSA plus etc. It was shown to be a contraction monotone. The unique fixed point value is the value of this two-day process. So this can be formulated as a linear programming problem. By writing this, you take TUS, you bring everything else to the RSA is the only fixed quantity. The other one is some u. So bring it to this side, and you can write it as a system of linear inequalities. And so you can write down the following linear programming problem. Minimize summation US subject to these inequality constraints. Subject to these inequality constraints. So it was Blackwell who, it was not Blackwell. This was not done by Blackwell. Blackwell did only policy improvement algorithm. You see, one is to think of each time two types of algorithms. In pure maximization or minimization problem, you can think of moving from one policy to another policy, adjacent policy, that is the policy improvement type. The second type is somehow reduce it to a linear programming problem and try to solve the linear programming problem and find the solution. Okay? The policy improvement is somewhat analogous to Newton-Raphson method, finding the root of an equation, something close to it, which is you start close to the answer, you go faster to the answer. That is a policy improvement. This one is by solving through the dual, etc. This is the second one. So this problem, Markov decision process, can be done by both ways. Okay? There are advantages sometimes to this, advantages sometimes to the other one. But by and large, that is much faster. Experimentally, you can try the two things. The policy improvement is a much faster approach. So the solution to the problem depends on the dual to the linear programming problem, and that can also be written in this fashion. Okay. Now, one thing which I can do, see, it is not easy to immediately follow everything. Any student who can follow my English, that's important. See, if you know the Brazilian language, that doesn't help me. It doesn't help you also following my English. If you can, then I am willing to spend the whole, I am here till August 2nd. Because I have seen Brazil and also the trip to this and that and everything. and Iguaco waterfalls. All that. I have seen with my family. I have absolutely no interest in any vacationing. I have come only with the idea of finding at least one or two students who may pick up something out of what I am trying to, what I have done, and what my colleagues have done in the field. The ones you can pick up, then you have a chance to work on that. I can suggest also the explicit open problems and everything. But what it needs is somebody who is willing to spend the time with me. I have no interest in attending any lectures, nothing, because I'm too old for now learning new things. I can only impart the past knowledge, okay? Not the bookish knowledge, but something where I am myself struck up, I couldn't proceed any further. Okay? I have struggled hard, and that's what it is. For example, my former student is Brian, and he was one of the persons who went into a totally different direction, even though he knows whatever I am speaking. And then he pushed. This was in 2016. Okay. But after that, for 3 years, I've been only trying to run game theory in my village in India. Pick up students from, best students from different universities, suggested by the professors. See, suggested by the professors. And then I spend my personal money to accommodate them and to give them free food and also give the free education. So this I was doing for 3 years, 2017, 18, 19. 19, COVID came. So after that, I couldn't do. But then in the last 3 years, again, I have been doing it at different universities in India. Main idea is wherever I want to give such a lecture, I put the first constraint on the institution. I will pick up 5 students based on the teacher's recommendation and from the best institutions called IITs, IIMs, etc. And then spend the time with them in my village kind of thing, in the same atmosphere, even in the new place. I have no interest in even going here and there or anything. So like that I have been doing. I continue to do that one so that the knowledge must be transferred only on a one-on-one basis. It can't be done through remote all the time. Remote you can communicate, but you cannot formally teach them. Anyway, that is the spirit of this lecture. Okay. So, in some sense, these are the things: Markovian decision process, finite number of states, finite number of actions in each state, transition is Markovian, and the best strategy can be found by policy improvement and also by linear programming, by considering the linear programming and its dual. It is only through the dual you get the answer. So before you come to learn this field, you must be familiar with linear programming. Otherwise, you will not be able to proceed further. So you need the training in linear programming, properties of dual simplex method, etc., etc. That's needed for this topic. The next thing is what is called the main topic, stochastic games. So what is a zero-sum matrix game? A zero-sum matrix game is, you have two players, zero-sum two-person matrix games. You have two players. Player one chooses, they both are informed, a matrix A. Player one chooses secretly a row of the matrix. Player two chooses secretly a column of the matrix. And whichever entry is reached, that entry is paid to player one by player two. Maximizer receives the payment from the column player. So the aim of player one is to maximize his expected income. The aim of the player two is to minimize other players' expected income. And the theorem of von Neumann says there exists good way of selecting the rows with different probabilities called optimal probability, and similarly a good way such that no matter what the opponent does, player one can guarantee a fixed amount V, and player two also can guarantee a maximum loss at most V. That this V is called the value of the game. This V is called the value of the game. So the question is, if you play this game again and again, then you can, and you don't keep track of what you did in the previous game. You play repeatedly in this without watching what the opponent has done, what you have done. You only know the numbers. Then the best way of playing the game is to play the same way. However, if you know how to store the information, if the player, for example, the player 2 chooses a column, player 1 chooses a row, both players may know what has happened till now. So if they can use the history to change their strategy, they are called repeated games. So repeated games is something which is still working. People are working in repeated games. A stochastic game is one-order complex. One-order complex. In the sense, you play the same way, you can also keep all the information, everything, but it is discounted. It is discounted, for future is discounted. How to play such a game? This was taught for the first time by Lloyd Shapley. One minute. Let me, take a simple case. There are only two states. In state 1, if you choose the first row, and if the other player chooses the first column, player 1 receives $3 from player 2. And the game remains in the same state. 3 under 1 means the state reached this again, you play the same game. Okay? Suppose he chooses the first row and the other guy chooses the second column, then player 1 gets nothing, and the game moves to the state 2. In state 2, you get nothing. You get nothing in state 2. So how long you play, you get nothing. So it's an absorbing state. Suppose you have to play this game, how to play intelligently this game? How to play intelligently this game, and both players are thinking how to play intelligently. So what Shapley said was a following simple intuition. He says, I am going to seek the help of God to play this game. And then if he plays, if the game starts in state 1, he can get me for player 1 a certain amount B. If he starts in state 2, God cannot help. God himself cannot help, you get only 0. You get my point? Here in state 1, God can help you to get V for player 1, and player 2 must be willing to spend V, okay, by intelligent play. But in state 2, God cannot help. But God says, how are you going to learn how to play this game? You must at least play once, one day at least. First day you play, and whatever you collect, you keep it. From second day onwards, I play for you. But unfortunately, it will be a discounted value. So what he says is, if the game starts in state 1, if I play for the first day, I collect, say, 3, provided he chooses column 1, and beta equals 0.5. Take the discounting is 0.5. From second day onwards, God plays. And he is able to collect V1. But unfortunately, it is only from day 2. So it is 3 plus 0.5 V1 is my expectation. Similarly, 0, if I started here and if he chose this, I get 0, and God cannot help me, it's same 0. Here it is 0, is this. Then when you calculate this, what God says is, if you know how to play this game, I don't have to help you. If you know how to play this game, I don't have to help you. Interestingly, if I write down this matrix and calculate its value, I can do one thing. This value is actually contraction. So I can get first time something, second time something, third time something, and it converges to a limit. Okay? For this example, 1 minute. Unfortunately, if I calculate the V1 and V2, it becomes minus 4 plus 2 root 13 over 3. So what happens is, the game, all the data, transition, everything is exact and rational numbers. But when you calculate the value, it becomes irrational. So that means the solution escapes out of the field of operation. The field of operation is only adding rational numbers, multiplying them, dividing them, etc., etc. It escapes out of it. So this is, if it is retaining in the same field, we call it an order field property, is preserved if the data defining the game, a problem, and a solution to the problem are in the same field. So only if you have that, you have a hope of solving such games. Otherwise, not much hope. You don't have much hope if it escapes out of the field of operations. So this was, in fact, what happened was, I had my colleague T. Parthasarathi. We both used to work from 7th grade together. Even for any student, my advice is, you try to work with one more person. For the simple reason, between you have a competition. And between you, you are working together, you try something and you are exhausted. He is not exhausted. He is also pulling on for some more time. And he comes with his own struggle. Then you continue. So you do this one by one, and in the long run, you are going to actually solve the problem or realize that this is not solvable. So this, my friend who has done the theoretical part, I asked him, can you compute the value of this game? He didn't know what to do. I said, then let us work together. Simple 2 by 2 we took, same game, and realized there is no hope. Okay. Then we decided, the part of the reason is both players are controlling the transition. See here, for example, when I choose row 1 and you choose column 1, we both influence what is the next state. So when I choose row 1 and you choose column 2, we both influence what is the next state. So when we both of us are responsible for the next state, it brings the hopeless situation. Instead of that, suppose we assume only one player is everywhere. So here we consider the special class of discounted stochastic games where only one player controls. That is the game we started in 1978, 79, around that time. Okay. But then we tried to solve that class of games, but I had a student, and then I asked him, even though I do those things, let us take a simpler class, a class of games called perfect information games. So what are they? In each state, one, yeah, okay. 4 more minutes? Thanks. I will stop here. Okay. I can even stop right now and start tomorrow. 4 more minutes. Okay. So I had a student and who came, and there was another researcher from Netherlands, okay, Frank Thijsman. We spent on a special class called the perfect information. What are perfect information stochastic games? These are games where in each state, only one of them has any action. The other person is a dummy. Okay? He doesn't have any action. So this player's influence will transform the game from one state to another state. But the other state may be a state where you are a dummy and the other player is the main one who has action. So other player's interest is to minimize your long-run discounted income. Your interest is to maximize your long-run discounted income. Should I choose this action or that action? This becomes a Markovian decision process. This problem becomes a special Markovian decision process. And so how to use the knowledge of policy improvement in Markovian decision process to improve this case is the issue, and we didn't know how to proceed further. We were struggling, and I had a new student who came, and I will talk about that work next. Okay? Thank you.
Are there any questions? We have still time for maybe 1 or 2 questions. Well, if not so, thank you, Professor Raghavan.
Yeah, it's right here. So let's see how to remove it.
You can store the whole thing also inside.
I can what the whole thing?
You, that whole lecture, I have everything there. Or should I bring again this one? Okay, I will
It's
bring
better. It's
But-
better because at the end of the day, when
Yeah.
they turn off the computer,
Yeah.
All the files are
Okay.
removed,
Okay,
deleted.
okay.
So yeah, you better
Yeah.
bring it. So I understand it's been a hard time
Yeah,
to
yeah.
get here.
Sure. Really? You know what happened?
Visa.
They were delaying with the visa. And
Yeah.
I haven't got the visa. You know what they tried to do? They wouldn't allow us to go to the consulate. And then with a lot of struggle, I got to take Malaysia.
Tem que pôr intervalo. Intervalo no YouTube. Intervalo no YouTube. Põe intervalo lá no computador. Intervalo no VMix. Conseguiu?
Peraí.
Som.
Tá, ok. Aparentemente, assim, do retorno normal.
Tudo bem?
Hi. Hi, Professor. Do you hear me?
Hello. Do you hear me?
Yes. Your?
Yes, yes. Just join from browser. Okay, just let me see if I'm joining you.
Will you be sharing your screen with like a presentation or something alike?
Just a moment. Joining meeting. Okay.
Okay.
Now.
Uma vez que ele coloque os slides, já a imagem vai ficar pequenininha.
Okay.
Agora ele está entrando pelo aplicativo ou pelo navegador. Não, vai ter que fechar o outro. Senão vai ficar dando.
Okay.
Could you please mute one audio and because you're having like a loop through the two entries in the meeting.
Do you hear me?
We can, but you gotta close one of the connections.
So what do I have to do?
No, the other one you entered, are you gonna use it for anything?
What do you mean the other thing?
Okay, I removed the other one.
What is the other one?
No, you enter like with a second login in the meeting, but I just removed it.
I see. Okay.
Could you tilt your webcam a little bit down to better enclose your face like in the meeting? Just a little tilt.
All right. Okay, join meeting. Right, personally. Join meeting. Meeting or personal cancel. I don't know. I don't know how to sign in. Email or phone number. Sign in.
No, you are already signed in.
So where? What do I see? Where can I see something? I don't know. You may stay signed in longer. This device learn more.
Aren't you seeing like a small square with us, like a peep of our webcam?
Now,
Strange.
sign in. So let's try again. Okay. Cancel. Okay, do you hear me?
Yeah, we can hear you.
Okay, now I can hear you and there is no echo. Okay. Let's see if you.
Could we try the screen share test?
Okay. Share. Okay. Share.
Okay, we can see your screen.
And You can see?
Yeah, we can.
Okay, good. So we did it in 5 minutes. Okay.
Yeah. Thank you. We are gonna mute just for like this next 5 minutes, and then we will open the channel, okay?
Okay.
Ou clica aqui, ou Alt A, ele desmuta, tá vendo? Ou clica só no ícone, tá bom?
Para comenzar, ¿comenzamos a qué hora, sí? ¿Ya comenzamos ahora o...? Mais 5 minutos. Mais 5 minutos?
Todo mundo está no classe 10, não é?
Ah, tá.
É 10 ou 10, né? Ou é 10 e 5?
Aqui está escrito 10 e 5.
DVD. Mas o pessoal está tudo no café. 5 minutos, 4 minutos.
Eu banho.
Next semi-plenary session, semi-plenary lecture. Just a little announce. This event is being broadcast live and recorded on YouTube. By remaining in this venue, participants acknowledge and agree to the capture and use of their imaging and voice in the broadcast and recording of this event. Well, now we're gonna start with the semi-plenary lecture given by Professor Dov Samet from Tel Aviv University. Interpersonal Independence of Knowledge and Beliefs. Welcome, Professor Dov Samet. Can you hear me?
Thank you very much.
Mm-hmm.
Do you hear me? Yes.
Perfect, perfect. Everything is fine. So please start with your lecture. You have 50 minutes.
So, okay. Interpersonal logical relation of knowledge and belief. There are too many things that are involved here. There is interpersonal, and there's knowledge and belief. So we are not dealing with the logical relations of knowledge and belief, but rather the interpersonal for knowledge and interpersonal for belief. So this is a paper by Ehud and myself. So it's interpersonal, which means that there are at least where we have two persons, two individuals, Anne and Bob, and she's number one, and he is number two, and we are talking about the relation between their knowledge, one thing, and the relation between their beliefs. Okay, so here is the question we ask. Can two descriptions of knowledge of person, individual one and individual two, be equivalent? And by equivalent, we mean logically equivalent. And the answer is very simple, of course. You want an example? Here's an example. One knows F or not F, and two knows G or not G. These two sentences are logically equivalent. Why are they logically equivalent? Because F or not F is always true, and therefore one always knows it. And in the same way, two always know G or not G. And since both sides, right and left, are always true, they're logically equivalent. So the answer to the question, can descriptions of knowledge of one and two be equivalent? The answer is, of course, yes. Or we can have another. Here are two examples where this not K1, so this is always false, and this is always false. Also, two knows G, doesn't know G or not G. Well, of course he knows, always, and therefore not K2, G or not G is always false. So the two sides are always false, and therefore they are equivalent. And the same way here is K1 knows something which is always true, K2 knows something which is always true. They are logically equivalent. So that's not a good question. So the good question is the following. Can non-trivial, so I'm sorry. Okay. So what is common to all these examples is they are always, the left side and the right side are always true or are always false. And therefore they're equivalent. So they are trivial in a sense because they are always true or always false. So the question is, can non-trivial descriptions of knowledge of one and two be equivalent? So these are not examples because they are all trivial. They are always true or always false. So something which is not always true or false, always true or always false, are there non-trivial descriptions of knowledge of one and two that are equivalent? Can I answer questions or? Okay, nobody to talk to. Okay. Can non-trivial descriptions, so this is a question about knowledge. Here is a question about belief. The same question exactly, but instead of knowledge, belief. What is the difference between knowledge and belief? For our purpose, the difference is the following. Knowledge is if KF, if F is known, holds, then F holds. Knowledge is something that is always true. And belief is not necessarily always true. BF may be hold, while F does not. One believes F, but F doesn't is not true. So this is the question. So here is another question. Can a description of knowledge of one, can it imply a non-trivial description of knowledge of two? So the question is about knowledge, but not equivalence, but rather implication. The knowledge of one implies a non-trivial description of knowledge of two. And the same question about belief. Okay. So here is a summary of there are really 4 questions. Are there non-trivial F and G describing one's knowledge, this is F, and two's knowledge, this is G, such that, so here is knowledge, there are 2 questions about knowledge and belief. So are there non-trivial F and G describing 1 and 2's knowledge or 1 and 2's belief, such that F is equivalent to G, F implies G. So 4 questions. For knowledge, can we have F and G that are such that F implies G, logically implies G, and F is equivalent? So 4 questions. Note that if there is something that such that F is equivalent to G, then of course there is F implies G. And conversely, if there is no F and G describing 1 and 2 knowledge or belief such that F implies G, if there is no F and G, then of course there is no F that is equivalent to G because equivalence implies implication. Okay. So knowledge. For knowledge, the answer is yes. So here is F is 1's knowledge, describing 1's knowledge. G is describing 2's knowledge. And F logically implies G. Is there some? Yes. So the answer is yes. But I mean, you cannot participate in this talk, right? I mean, I cannot ask you a question. Okay. So KY, 1 knows that 2 knows E. What does it imply? It implies that 2 knows E. If 1 knows, then everything that 1 knows is true. And therefore, if 1 knows that 2 knows that E, then 2 knows that E. So the answer here is yes. Here is another example. If 1 knows E, then 2 cannot know not E. Okay, so a knowledge of E, of 1, implies something about the knowledge of 2. Okay. F implies G. Is it possible here? The question now here is in this empty box. Is it possible that F describes 1's belief, G describes 2's belief, and F implies logically G? So the answer here is no. It is impossible that the belief, a description of 1's belief, implies logically a description of 2's belief. It's not very surprising because belief is not related to maybe it's not so trivial because a description of F about the belief of 1, a description of 1's belief implies something. For example, it implies 1's beliefs. So there is some relation to reality. And if this is no, we will show that why there is no here, but it implies no in the box below. if there is no F that implies G, then of course there is no F that's equivalent to G. Okay, so now I want to show that here we have no. Let me say again, what does it mean? There is no F and G describing one's belief and two's belief. That is, F describes one's belief, and G describes two's belief. I'm sorry. There is no F and G such that F implies G. Okay, so first of all, let's recall knowledge. What is knowledge? We start with an algebra, which is a set closed under intersection, and these are two symbols, that's all, and negation. What does it mean that is closed? If F and G are in the algebra, then F intersection with G and the negation of F are in the algebra. What else? The algebra is with knowledge. If for each agent I, the algebra is closed under Ki. So if F is in the algebra, then KIF is in the algebra too. The algebra is of descriptions of events in the minimal algebra with knowledge that contains the basic events in the set script B that includes E, F, G, etc. So let me put it, let it read me backward. There is a set of events, basic events, E, F, and G. I mean, they are just call events, but there's no model here. This is just an algebra of descriptions. So there are basic events in the set script B, E, F, and G, and the algebra is closed. You take intersections and negations of the elements of B, and then you continue over and over again, and this is the algebra with knowledge. Okay, so here is an example of something that in the algebra, right? It's okay. The algebra generated by descriptions of the form KIF is the algebra of descriptions of I's knowledge. So this is not in the algebra of I's knowledge, because you see you have here K2 and you have here K1. So it doesn't describe one's knowledge and it doesn't describe two's knowledge. But if we take the K2 negation K2F, if we erase it, then we have something that starts with K1. It describes one's knowledge. Oh, I see that, yes. So here is, it's the same line, only that instead of K2, we have K1. Okay, so now it describes one's knowledge. Okay. Okay, so these are only descriptions of events, and now descriptions of knowledge for 1 and 2. And now these descriptions are interpreted in a model. So a model M consists of the following elements. You have omega, you have a function, brackets, and you have a partition for each individual, pi I. Okay, so omega is a set of states. Here is omega. The function, the bracket function here is a function from the basic events P into 2 to the omega. So here is an example. This is the initial assignment. So here is E. You see, bracket E is the event in omega. It's a subset of omega, and here is a subset of omega, which is F. And we have for every how did they call B? Basic events. Okay, so for each basic event, we have interpretation. And Fm, that is bracket F, is M, and M subset is the event in M corresponding to the formula F. So it has the following properties. If you take F and G and you ask how are they interpreted in the model omega, in the model M, so it is the intersection. If F and G were already interpreted, then F intersection G is the intersection of the interpretation of F and G in the model M. And the formula not F is interpreted in M as the complement. This sign here should be interpreted is part of the formulas. It's part of the language, but here it is the complement, the set complement of Fm, of the interpretation of F in the model F. So here is F, the interpretation of F in the model M. This is omega here, that you can see omega, and you can see the interpretation of F in the model M, and we say that F is true at omega. Okay, so F is this, Fm, and it is true at omega. Okay. On top of it, there is a partition, I's partition, pi I, a partition of omega. And here is, for example, if we have Fm, if the interpretation of F in the model M is the framed, black framed box here, then, and pi I omega is the element of the partition, of the red partition of I that contains omega, then KIF is interpreted in M as the set of all omegas such that pi I omega is a subset of M. So forget this complicated formula. This is KIF of M, okay? Because this framed, red framed box is a union of the elements of pi. And this is the union of the elements of pi that are contained in F, in the formula, in the interpretation of F at omega. Okay. Now, what does it mean that F is trivially true? F is trivially true if in every model Fm is all of omega. So example of a formula that is trivially true is something F or not F. It's trivially true because in every model it is interpreted as omega. So G or not G is trivially true. KIG union G. This is trivially true because it is interpreted as KIG, subset of G. I'm sorry, it is interpreted as not the complement of KIG union the complement of G. But to say that it's always, but to see that this is always, that this is trivially true, you know that KIG, the interpretation of KIG is an event which is a subset of G. This by definition of the definition of knowledge. So this knowledge is always truthful, that's by definition, and therefore this is trivially true. F is trivially false if Fm is the empty set. So the interpretation of F in a model M is always the empty set. So for example, the complement of this is always true. The complement is not a G intersection with G. So this is always empty. KIG intersection with not G. That's just the negation of this one. Okay, so F is trivial if it's either trivially true or trivially false. F is consistent if it is not trivially false. So, for example, here is an example. F is consistent. It is simply, this is simply always true, and therefore it is consistent. KIE, E is a basic event, is not trivially false. There are models in which KIE is true. So here is, you have the set of descriptions. You have trivially true. You have trivially false. You have non-trivial. Okay, so all these formulas are non-trivial. And this is consistent. It includes all the non-trivial, but it includes also the trivially true, but it doesn't include the trivially false. Now, what does it mean F implies logically G? It means simply that the event that corresponds to F in the model M is subset of the event that describes G in M, and this is true for all models M. So the event described by F is always a subset of the event described by G in all models. Another way is to say that not F union G is trivially true. That's the same thing as saying this. And here, F is logically equivalent to G if F in the interpretation of F in model M is the same as the interpretation of G in model M for every model in M. And this is equivalent to say that F implies G and G implies F. Okay, now I want to define belief. So a model for belief consists of omega. Up to this point, it's the same as in knowledge. There is a set of states, interpretation, and a partition I, but there is also a set sigma I. Let's see what it is. So there is a partition. Sigma I is I's supports. So the cardinality of sigma I and the cardinality of pi I are the same, and each element P of the partition pi I contains one element sigma IP of sigma I. Here it is. Here you see, so this is sigma I, the round shapes are elements of sigma I. You see that every element of pi I contains exactly one round figure, which is, so the elements of the round figures is called sigma I, and sigma IP, if you take P, the first element, rectangular shape here contains sigma IP. Okay. So you have pi I, you have sigma I, as we explained, and look at this event, the black one, the black triangle, and BIF is simply the set of all sigmas that are in FM. So forget the formula and look at the picture. You see that there are 3 boxes such that the round element in each box is contained in the black triangle. But if you look at this one here, if you look at the last one, then the round shape is not even included in the black one. But you look at the third from the last, you see that there is some intersection of the black triangle and the round shape, but the round shape is not contained. So the only boxes that contain the round shapes are the first three boxes. So BIF is just the red box here. belief is not truthful because, as you can see, no, I don't say, okay, it's not truthful because BIF is not, if you look at, okay, you can see that BIF is not included in F. And now the question I pose is the following. Are there a non-trivial description of one's knowledge and a non-trivial description, the blue G, of two's knowledge, such that F is equivalent to G? If no, knowledge is interpersonal independent. So you see the independence we are talking, it's independence across individuals. So if there is no F and G, non-trivial F and G that describe one knowledge and two knowledge that are equivalent, then knowledge is interpersonal independent. And the same goes for belief. Here is question, are there a non-trivial description of one's belief, yes, rather than one's knowledge, and non-trivial description of two's belief, such that F is equivalent to G? And if no, then belief is interpersonal independent. And now we replace the F in equivalent to J by F implies G. We replace the equivalence by implication, and if there is no such F and G, the knowledge is, let's see what it is, strongly interpersonal independence. Because strongly, why it is called strongly? Because it implies interpersonal independence. If there is no F and G such that F implies G, that clearly there is no F which is equivalent to G. And here too, if we replace F imply G, then if there is no F and G, then belief is strongly interpersonal independent. Okay, so here is a theorem. If F and G are consistent descriptions of one's and two's beliefs, consistent descriptions means that each one, F and G, are true in some model. That's the definition of the consistent, or we defined it before. So if F and G are consistent descriptions, there are models such that one model in which F is true in some state and G, some other model where G is true in some state, then the intersection is consistent too. That's not, it's a non-trivial statement. You'll see immediately why it is true, but that's not clear that F, for example, it's not true for knowledge. F and G can be consistent descriptions of one and two's knowledge, but F intersection with G is not consistent anymore. For example, one may know that 2 knows E. It's consistent. No problem to produce a model. E is a basic event, so there is no problem to describe a model in which F is consistent, and G will be 2 doesn't know E. No problem to build a model in which this is true. But the intersection says that 1 knows that 2 knows E, intersection with 2 doesn't know E. Well, this cannot be consistent. But for belief, it's true. Okay, so how do we prove it? We first define the depth of a formula. So if you look at the depth of a formula in the algebra generated by the basic events, so E, F, E intersection with F, not E. So that's the algebra generated just by the basic events. The depth of such formula is 0. The depth of a formula BIF is the depth of F plus 1. Okay, so it increases application of the of BI increases the depth of a formula by 1. The depth of F intersection with G is the maximal of the depth of F and the depth of G. Okay, and finally, the depth of negation of F is the depth of F. Okay, now here is a theorem. For each k greater than 0, greater or equal 0, we build a model MK such that for all consistent F of depth less or equal k, in the model MK that we build, FMK is different from the empty set. Okay, so this is a model in which all consistent formulas of depth less or equal k are true in some state omega. Now here's the important part. For all f and g of depth less or equal than k, so we know that that f is true in some state and g is true in some state, as we said before. So if f and g are consistent descriptions of ones and twos belief, then f intersection with g in the model MK is not the empty set. In other words, so if f and g of depth are less than or equal than a are consistent, then the intersection of f and g is also consistent in this model. Okay. Okay, for k equals 0, let's see, and I think that this will be simple. Omega 0 that's the set of states of M0. The atoms of the algebra generated by B. So, in other words, B is simply E. Okay. No, I'm sorry. The algebra is, so this is an example of a model. The case of that there is only one element of the basic events, E, and omega 0 is going to be E or not E. So omega 0 is the atoms of the algebra generated by B. B has only one element, E. The algebra generated by B is E and not E. There are no other events. I mean, okay, of course, no, omega 0 is just these two. Yeah, okay. K equals 1. So omega 1, so now I'm describing the model M1. It's omega 0 intersection with S1 sub-0 and S2 sub-0, where S and S1 and S2 superset 0 is the set of all events that are not subsets of omega 0 that are not except the empty set. So here is the omega 0 is E and not E. So this is the omega 0. S1, so I'll write only the S1 and you imagine, you complete it in your imagination. So S1 super 0, the red one, is E, not E, E and not E. All the subsets of omega 0 that are not empty. So there are omega 0 times E, not E, E, not E. There are 6 elements in the model. Okay, now E is the, okay, I'll show you what is. So in this set, I circle E. In this set, I circle not E, and in this set, I circle E and not E. Now, so this is the model omega 1. It's omega 0 times S1 times S2, which is not presented here. So in this element B1E, so this is the, remember the events sigma. So this is a partition. The boxes here, and the circles here are the B1. This is B1 not E, and here it's not B1 not E and not B1 E. So here the you don't know whether E or not E is, you don't believe neither E, neither not E. Here you believe E, here you believe not E, here you believe E. And then you define it by induction. And in this model, you can show with a little effort that what is written here is true. So in each model, MK, every consistent F is true in some state, and if F and G are consistent, then their intersection is also consistent. Okay. Theorem. No, we proved it. If F and G are consistent descriptions of 1 and 2 beliefs, then F and G, F intersection G is also consistent. We proved it. We take K such that the depth of F and the depth of G are less or equal than K, and then we have shown that if F and G are consistent, then there is a model in which F and G are true in some states, and F intersection with the G is also true in some state. Now, let's look. If you take G, which is non-trivial, then not G is consistent. If not G is consistent, then G is trivial, because if not G is not consistent, it means that it always false, and therefore G is always true, therefore G is trivial. So not G is consistent. Now, take not G is consistent, F is consistent, then the intersection of F and not G is also consistent. So in some model M, F intersection with G in the model, in not G in the model M is not empty, is not the empty set, because it's consistent. Therefore, the event corresponding to F is not a subset of the event in this model M, is not a subset of the event G. And therefore, F does not imply G, because for F to imply G, it means that F is a subset of G in each model M. But here we see a model M where it is not true, and therefore F does not imply G. So we have shown now this. In this, we have shown the that belief is strongly interpersonal independent. Okay, so we had before a table. There was no here, but because here we talk about strong interpersonal independence and interpersonal independence. Sorry. Okay, so there was no here and yes here, but we are just stating the independence. Okay. So now the question is, the remaining question is, what about knowledge? there's no strong interpersonal independence, as we've seen, that this is trivial. But is there interpersonal independence? Strong interpersonals is F imply G. So we saw that we have F imply G. K1, K2, something implies not K2, not the. So the knowledge of one implies something about the knowledge of two. But now the question is whether there is no implication, or not an implication, but rather equivalence. So it turns out that interpersonal independence here also there is interpersonal independence, as opposed to strong interpersonal independence. Interpersonal independence exists. Now, so let's prove it. Interpersonal independence of knowledge. There are no, here's a theorem, there are no non-trivial F and G describing one's and two's knowledge, respectively, such that F is equivalent to G. Okay, so you cannot describe in a non-trivial way one's knowledge, F, and describe two's knowledge, G, such that F and G are always logically equivalent. You can't do it. Why? So what does it mean, F equivalent to G? Which means in each model M, Fm, the interpretation of F, which is a description of one's knowledge, and the interpretation of G, which is two's knowledge, are the same. Why is it so? So here we need the notion of common knowledge. Common knowledge partition in the model M with two agents for is the partition pi cm. Okay, C is for common knowledge, M is the model, which is the finest among the partitions that are coarser than each individual partition. That's a complicated sentence, but here is the picture that explains it. So here is a partition, the red partition for, let's say, player 1. Here is the blue partition of player 2. So there are two players, and there are two partitions. Do we have a partition which is coarser than the red one and the blue one? So the answer is, of course, there is one such a partition, the whole state. But is there a finer partition? The answer is 2. Is also the, okay, here is the black one into 2 elements, this one and this one. So there are only 2 partitions here. One is finer than the other, and therefore the finer one is pi cm. So the common knowledge operator KCM is defined by pi cm. So pi cm is the common knowledge partition, and with this partition into 2 elements, we have associated knowledge operator KCM, and yeah, that's it, KCM. Now notice, if Fm equals Gm for each model M, then we have an event which is described by one's knowledge and described also by G knowledge. In other words, this event, the same event here, is partitioned into by the partition of the first player and by the second player, and therefore we can say the common knowledge of F is F itself. Okay, so in each model, F and common knowledge F are the same. Theorem: for each non-trivial F, there exists a model M in which KCM of F is not equal F. So we said that this, to prove the theorem claims that F and G in each model are the same. And in particular, it implies that F and KCMF is the same event in each model, but we show that there is F such that this doesn't hold. KCMF is different than F, which shows that the theorem is correct. There is no non-trivial F and G such that F and G are equivalent. Okay, how do we prove it? That there is a formula F, which is the common knowledge of this formula is different from the formula in some model M. We defined a metric on M. Omega and omega 2, omega 1 are adjacent if they are in the same element of pi I. So if we can write omega is adjacent to omega 1, and I write here I to say that they belong to the same element of the partition of I. Here is an element of the partition of I, and omega 1 are in the same partition. Okay. So now I take another omega 2, which is adjacent to omega 1, and this time by J. So there is an element of J's partition such that omega 1 and omega 2 belong to the same element of the partition. So here we say that omega and omega prime are connected if omega 1 is adjacent to omega, and omega 2 is adjacent to omega 1, and so on up to omega prime. So omega prime and omega and omega prime are connected if we can go from omega to omega prime. So each time we are in some element of one of the partitions. A model M is connected when all pairs of states are connected. So we defined what it means for omega and omega prime to be connected. And now we say when is the case that M is connected? And the answer is whenever all pairs in omega are connected. M is connected if and only if MCM, the partition, the common knowledge partition in M, is omega itself. So in other words, you don't have a sub model that is connected. The omega prime is the minimal number of states required to connect omega and omega prime. And this is a metric. So we have now a metric. So this can be, the interesting case is just the case where omega is, where pi c omega is omega. Otherwise, you have also distances which are infinite, but in any case, we're interested only in cases where pi cm is omega. We create a new model from two models, M1 and M2. We glue them together. The state space of M is the union of the states of spaces. So here is omega 1, here is omega 2. the initial assignment in M is the union of the assignment. So if you have an assignment in omega 1 of E, and you have an assignment of omega of E in omega 2, then the assignment of in omega 1 and omega 2 is the union of the two assignments. It's simply this. The partition in M is the union of the partitions, except that we take an element, we choose in each model an element of the partition of the same agent I. So here is one element, and here is one element of I, and we erase the wall here so that now they are the same. It is one element of the partition. If M1 and M2 are connected, then the glued model M1 omega 1 union omega 2 is connected. The assignment function omega 1 and omega 2 has changed. Okay, the assignment function has changed because now in this element of I that is depicted here in the picture, then of course we have a different interpretation of things, and therefore the whole thing is changing.
Professor
Yes. Yes.
Could you? We have to start with the next session, so
okay.
we will appreciate if you could.
What is it?
If you could enclose your presentation. We have a new session now.
Okay. Okay. So I'll in 1 minute. Yes.
Okay. 1 minute. Perfect.
Yes. Okay. So now you see that you can increase arbitrarily the size of a model. We take a connected, if F is consistent, we take one model in which F is connected, and the other model is the mirror image of omega 1, and we take the mirror image of one element of the partition, and we have a new, because it's a mirror image, it turns out that the interpretation of sentences doesn't change much, so we can have as big model as we wish, in which F is true, and the other thing that we show that the restriction of omega to a ball of radius of the radius of the depth of F is the only thing that determines the truth of F in omega, and therefore we can have a connected and two models that are connected in which F as big as we wish, in which F is true and not F, because F is non-trivial. There is a model in which not F is true, and we can take the union of the two models, and of course you can see that in this model F is not always true, because not F is sometimes true, and not F is not always true because F is sometimes true. So in other words, this is exactly a formula F such that the common knowledge of F is not F itself, as we promised that we can do. Okay.
Well,
that's it.
Thank you very much, Professor.
You're most welcome.
Unfortunately, we will not. We have no time for questions, but anyway, thank you once again, and we are going to continue with the next session. In fact, it is a mini course from Professor Hervé Moulin. Então, I think this is what.
I put it this morning, but I don't see it. Ah,
It's in the. Excuse me.
yeah.
Just two quick announcements before we start the next session.
Yes,
First,
yes, no, the second
someone
one. This
forgot
one, yeah.
a hotel card
Okay, good.
somewhere, and it's in the secretary. If you can, please take that. We will be happy. And the second one is that the room A4 in the same corridor of the regular sessions is open with internet and computers for those who want to use them. That for those who don't have computer here, it's again room A4. Thank
I
you.
tried it, but.
And where do you change the? That's okay. I don't care. Where is the click to change the thing?
Oh, it's
here?
over here on the arrow.
Here. Yeah. No, it doesn't.
No, it doesn't work.
Yeah.
Well, we need the help of
Excuse me, please. It's stuck. Travou? Travado aqui. Fecharia. Travou. Travou com tudo. Demorou.
And now
Move the arrows.
the question is whether.
The right.
Okay. Yeah. Thank you very much. Please let me know when my time is.
Okay.
5 minutes.
How are you?
Is this working? Yeah. Thank you very much for being here. And I want to talk about fair division, but I would like to be able to click. The click doesn't seem to work again. Can you? I don't know.
O aplicativo tá travando aqui, não sei porquê.
Why do you click now and I cannot?
I'm not sure. I think it's working again.
Okay. Let's hope. Don't go too far because you have the magic finger.
I stay right here.
It's a little bit like the piano.
Sorry, excuse me. Can you use this one, please?
Okay.
It's,
Can you? Okay, that works. Oh, wow. Okay. All right. So fair division. The first thing to note, of course, about fair division is, on the one hand, it's. Okay. First thing to note about fair division is the fact that it's ubiquitous in not only social sciences, but I would say social contexts. So I'm not going to go over that thing, but from the point of view of formal models, mathematical models, it's much more recent than other aspects of mechanism design, let's say, such as efficiency and incentive compatibility, which have been known for a long time. And for instance, Adam Smith's invisible hand tells us in a rigorous way, if you want, that efficiency and incentive compatibility can be compatible in certain contexts. There is nothing like that you can find in the literature about fair division in a formal, developed way. I don't know why. Maybe some references have been overlooked. We'll see. So game theory and microeconomics have contributed a lot to the topic of fair division. And those models, such as, Shapley value and other methods to share joint cost and surplus, axiomatic bargaining, etc., all those models are interesting. They all have common features with the specific subclass of models I want to describe now. But I'm going to have to be to limit myself if I want to give you a picture which has a minimal amount of consistency and hopefully a good amount. Let's see. It works.
Okay, so we'll be talking about the division of private commodities, right? In a model in which agents are essentially characterized individually only by a choice of their preference, for which they are held to be fully responsible. So in other words, the difference in their preferences justify some unequal treatment of this agent receiving unequal shares, because we have in mind, of course, the constraints of efficiency. So the second bullet, the agents have equal rights. The preferences are diverse. If they happen to have identical preferences, then they will be treated equally, at least from the point of view of their welfare. But if the preferences are different, they will not be treated equally, and we know that this is something we have to do because we know that this is implied by the efficiency concern. All right, and we can compare physical resources, but we cannot compare individual welfare. Examples, many examples, this divide an estate between the heirs. Agents break a partnership and they have to divide the assets. There is a commons, some kind of resources which is initially held in commons and is then divided in private plots. It could be a pasture, it could be timeshare of your workers, and so on and so forth. You know, if you go very far, minerals on the international waters are the common property of mankind, at least in a legal sense. And therefore, one day we will go beyond the law of the sea and actually implement the kind of mechanism that the law of the sea recommend, which have a lot to do, by the way, with divide and choose that is appearing in the lecture 3. I mean, today I'm going to focus on the competitive solution, the one which was introduced by economists in the 60s and early 70s, and I will do the blue sky aspect of this solution, namely the case, the extent to which we can be satisfied by this solution. Difficulties will start appearing in the second lecture when we think more carefully about incentives, and we also drop the monotonicity assumption. And then I will go into two different, slightly different, but in fact connected model, the cake cutting model, which despite the name, you know, the fact that when you think of cutting a cake, you say, oh, that's a very trivial example of the previous general idea of dividing commodities. In fact, from a mathematical standpoint, the cake cutting is the most general model of all. If you allow natural and general preferences. And then finally, indivisible object, that's the special issue, special type of concern which has been very important in this century, and in which the conceptual difficulties are the interesting part. Okay, AUDITÓRIO economies. So I think a lot of us know that. I mean, very quickly, we are talking about a mana, some bundle of divisible goods, infinitely divisible goods. K is the dimension of the space. It will essentially disappear, not appear very much here. The domain of AUDITÓRIO preferences that I write as AD are ordinal preferences over the box from 0 to omega, and they are continuous, monotone, and convex. Okay. And an allocation simply divides the bundle omega into non-negative shares, Z1 to Zn. Okay. So that's not problematic. And we start with the first model, the first test of fairness, the one that was introduced initially by a mathematician, I mean a group of mathematicians, Steinhaus and company, who were, you know, thinking about the cake cutting, but their idea and the idea which since then has become in some sense the most important and the most basic test of fairness is the idea of an endogenous fair share. In other words, initially over these commodities we have equal rights, but that does not give us, to start with, any private right over any share of the commodities, right? But without even thinking about the difference in individual preferences, we can, as a proactive view of fairness, we can try to think of what is it that we can guarantee to each individual participant just based on the knowledge of his or her individual preferences. We know that the difficulty will be this multiplicity of individual preferences, which can vary anywhere in that domain. We know the domain. So now we think, okay, if I think of something I call the fair share, which takes an individual preferences and, of course, the consideration of the resources to be divided, as well as also the number of agents involved, is it possible to define a mapping, a level of welfare, and this is going to give me a level of welfare for each individual preference in such a way that this level of welfare is always feasible. And you see, the key thing is that the level of welfare that you guarantee to an agent only depends upon his or her own characteristic, own preferences. So this is a way of, if you wish, helping agents to participate, to accept the participation in the division mechanism, because they know that they are not going to be risking to leave out empty-handed. There will be something for them. Okay, and that's also another interpretation, is that this is something that you can be guaranteed of, even if you don't participate in the mechanism, even if you don't try to bargain or whatnot, you just report your preferences properly, individually, and then whatever the mechanism does, you are guaranteed that level. So this raises, of course, a mathematical question. What is the best definition of this mapping, namely the mapping that would end up as high as possible? And because it is a function, we are talking of a function from individual preferences to a welfare level, which would be maximal in the sense that cannot be improved for each and every possible preference. So that's the notion of fair share. Make this profile feasible and push that level, that function, as high as possible in the sense of maximality. Okay. For the Arrow-Debreu model I just started with, this is going to be a very simple question with also a simple answer, which is equally well known. The test will reappear in all of the further discussion, the other lectures, and there sometimes it's going to become extremely difficult and even totally opaque in terms of what it can do. But here it's very simple. In the Arrow-Debreu model, your best possible fair share is simply to give you the level of utility. Utility is here, and don't take it cardinally. It remains all ordinal, but in order to describe things more simply, I use utilities, but it's always only ordinal. So in this model, it is feasible to give 1/n of the divisible resource to everybody. So this is a feasible fair share. Now, Why is it the best one? It's because any other fair share inevitably is below. Because when I say that this welfare profile is feasible, in particular, if I am agent 1, this welfare profile must be feasible if everybody is like me. So if I have n identical preferences, n people like me, and now we are trying to treat equals equally, because now we are all equal. And what can we do? Well, we can do omega over n. Of course, it's very fair, but it's also the best we can do. There is no other division of the commodities which will allow everybody to get at least that level and someone strictly more. But notice that this statement, that I cannot improve over 1 over n of omega for everybody in this domain, strongly depends on the convexity of preferences. If preferences were not convex, it would be sometimes possible to do more. I mean, think of a utility for 2 commodity where your utility for the pair A, B, the amount A of good A, B of good B is the max of A and B, then of course you can do better than split equally the commodity between the 2 of us. You get the first, I get the second, and everybody's. So here, in this model, there is no ambiguity. It is the best, and we don't have to worry about it anymore, but we feel very strongly for this fair share. I mean, it's basic, it's simple, and it is, in fact, the literature, all the work of the literature has been clear in identifying both the fair share test and the second test, much more modern, much more recent, of envy freeness as the 2 major components on which we try to build and that we try to make function and be compatible with the other constraint, the efficiency and so forth. So envy freeness, this is a concept that you know, I'm sure most of you. I don't want to exchange my share with your share. Even in the Arrow-Debreu context, this is not logically related to fair share. But the key observation, which comes again late 60s, early 70s, is that in fact it's a very nice competitive notion in spirit, because precisely the competitive equilibrium, when you apply it to a very special initial endowment, which is the equal endowment, the competitive equilibrium does give you that property for free, because in the competitive equilibrium, each one of us is maximizing in the common budget set, because we made sure that the budget set is the same for everybody, and therefore it gives us all equal exchange opportunities. Here, exchange is not the right term. I mean, it's purchase opportunities, right? And that's, of course, what the envy freeness is saying. If I compare my shares to all the other shares of the participants, I get the best one from my point of view. So that's a very, very appealing notion. It's the ex-post counterpart, if you want, of the ex-ante fair share. I mean, it's something that you cannot enforce ex-ante. You have to actually see the realization of the outcome to say, yes, the test of envy-free is satisfied. Second good news, in the Arrow-Debreu model, such an allocation, the competitive equilibrium starting from the equal income, exists. And moreover, of course, it is Pareto optimal and it satisfies fair share, of course, because we start from an equal budget, so we all can buy the omega over n. Very good. Is that all? In a sense, I mean, you know, there was a moment, I think, in the early 70s, maybe a bit longer, where the idea was, okay, for the Arrow-Debreu domain, we are done. Let's think about other problems. I think that was a mistake because, and this, I'm not the only one. The fact is that this Arrow-Debreu model doesn't really work well for the competitive equilibrium. Let me qualify this. It certainly has a lot of virtues from a positive viewpoint, but here we are not taking a viewpoint which is positive. We are normative. We are just saying, give me your preferences. So far, there is no incentive compatibility issue here. Give me your preferences. I suggest to you, or maybe I enforce, a fair solution. So if the concept gives me a lot of choices, because there are many such equilibria, that's a problem. And in fact, there are some powerful theorems from the 70s, Debreu, Mantel, Sonnenschein, that shows you that you give me any subset of allocation. I mean, because of the demand function can take any shape, I can achieve as competitive equilibrium very complicated and very large sets. So it's not good. It's not good because it's not a good normative choice. On top of this, another thing you can say is that even if there is a multiplicity and you agree on one of them, I mean, to get a continuous selection is also not possible. So that's a problem. In addition to the fact that the Arrow-Debreu domain is extremely unrealistic. I mean, it's unrealistic to expect that individual agents will be able to describe a whole area, a whole collection of indifferences and so forth. So this is where we switch gear. Well, this is just a remark. I'm going to skip that one. Just to say that in this whole business of this first and second lecture, if preferences are not convex, you really don't go very far, because not only you don't have a good fair share, but you also very easily violate NV freeness. I mean, NV freeness is no longer compatible with efficiency. So forget about non-convex preferences. We will come back to that when we do indivisible goods. Okay, and now this is where we realize that there is an important theorem from the late 50s, in fact, but let's say 60s, 50s, which is a little bit buried, was a little bit obscured by the glory and impact of the Arrow-Debreu domain in its full generality, which indeed is remarkable because the set, but the Gale-Heisenberg model, when you have in mind normative choice of a compromise between those people with their individual preferences and no particular incentive issues, that's the domain you want. It's a domain in the subdomain of Arrow-Debreu preference where indifference curves are homothetic. So if you draw one indifference curve in the orthant, you have them all by homothethy from zero. Okay? So you could say, from the point of view of cognitive effort to reveal your preferences, I mean, Gale-Heisenberg is already not trivial because you have to trace a whole curve, but certainly it's orders of magnitude less difficult than doing this with Arrow-Debreu. Moreover, all the practical utilities that are used in empirical work, they always assume that. Notice, of course, that for a Gale-Heisenberg homothetic preference, there is a canonical utility representation up to a scaling factor. You will always represent it by a canonical utility, which is homogeneous of degree 1, ui of lambda z equal lambda ui z, which starts at 0 and is increasing and quasi-concave to capture the... And the simple examples, of course, linear utilities, Cobb-Douglas, Leontiev, CES, I mean, they are all of this type. Linear Cobb-Douglas Leontiev, I will keep as my main sub-examples. And then what happens? What happens is a really beautiful theorem, which goes back again, Gale-Heisenberg. Always the same Gale, and for those of you who are not economists and they see the name of Gale, they could say, oh, maybe there are different Gale. Well, there are other people who are economists and are called Gale, but here we encounter always the same Gale all the time. Okay, if in such economy, the CEEI allocation is unique, both from the point of view of price and welfare. You could have some indifferences, you know, but the welfare profile and the price are unique. They vary continuously, both with respect to initial allocation and individual preferences, whatever normal topology you put on preferences. Moreover, and that's where the surprise comes, and that's where, in fact, I think was the origin of their result. This allocation is the unique maximum of the Nash product of canonical utilities. So the first time you see that, I mean, certainly for me, you say, wow, what is that? How come, right? I mean, you're connecting a model which is totally resources, in which you just look at distribution of commodities and how are my preferences. And then all of a sudden now you go into the axiomatic bargaining with cardinal utilities, and the two are the same thing. So that's really great, because it always tells you that, you know, if you happen to be in a context where the only thing you know is utility profile, or if you only believe on the cardinal utility approach and ignoring any ways to arrive, which way we arrive at these particular utility profiles, then you have one interpretation of the competitive solution. So this is something I want to show you how it works, because it's nothing mysterious, but it's really smart. And so here gives you the key insight of why is it that it works like that. Okay, so I'm just going to show you why, if I maximize the Nash product, I get the competitive. Then, of course, you have to do the reverse and so forth, and it's not particularly more difficult. So let Z be the allocation maximizing the sum of the log of the UI of ZI. All of that is strictly positive, because remember, we start at 0, and when you do the Nash product, you have to give a strictly positive utility to each. Assume a good A is consumed by 2 or more agent ij, but not by agent k. At this maximum, it's a unique maximum, because we are maximizing a strictly concave function in a compact convex set. At this maximum, the partial derivative of ui with respect to good A and the partial derivative divided by ui zi, I mean the log derivative, is the same as for agent J, and is greater than or equal as this ratio for agent K. So let's call that the price. Let's call this common ratio of all the agents who actually consume A in the optimum. Let's call that the price of A. And now what I will check is why at this price they all spend the same amount. Okay, so I compute for agent I the scalar product P by Zi. So this is the sum over all A, ZIA, PA, where of course the sum is only over those A that I actually consumes, otherwise it's ZIA equals 0. So it's 1 over UI ZI of the sum of the ZIA multiplied by the partial derivative, because I replace PA by partial derivative and the UIZI in the quotient. So of course, now I apply one homotheticity, and I know that the numerator is exactly the denominator, right? It's 1. So therefore, they each spend exactly 1. Moreover, by the inequalities there, but this time applied just for agent I over any goods A, B, and C, agent I equalize his marginal utilities over the different good A, B. Sorry, his marginal rate of substitution is the same as the ratio of prices, and that's it. He's actually maximizing in the budget set, and that's it. So you see, it's really nothing if you want, but it's extremely powerful, extremely powerful. And since then, I mean, you know, in some sense, it becomes the golden standard. Oops, let me go. The golden standard of this competitive approach to fair division when you are dividing goods and preferences are homothetic and convex and so forth. How much time do I have left? Half an hour. Oh, very good, very good. So maybe we'll go early for lunch. Let's see. Now, here, so what I described to me, I mean, in a sense, I mean, this result, the Gale-Heisenberg and what it implies, I think of it for the standard case with no difficulties of the Arrow-Debreu as really the major solution. But there is, in the literature, a different viewpoint, which came about from an important subgroup of people who, in some sense, did not come at it from game theory, Mathecon, and so forth, but more from a philosophical viewpoint and so forth. I will not go into any details that I would not be able to give properly anyway, but it comes from the following observation. Okay, we have this nice envy-free story, that's nice, that's exposed and so forth. But let's take a different viewpoint on common property. What does it mean? We own these resources in common. So, well, in a sense, it means we have an amount of solidarity vis-à-vis those common property. If I am citizen of a country and the country is doing well, I expect that I should also be doing well. And if there is a shock, I mean, if there is solidarity in the country, everyone will suffer. I mean, that's, of course, at the level of a country, it's not realistic, but at the level of a small fair division problem, it does make sense to say, look, if I think of an abstract division rule, whatever it is, to give me the profile of preferences, the resource, and I'll give you the rule. Think of the axiom of resource monotonicity. It says, if all of a sudden we have something better, more valuable to divide, because these resources have increased, and remember, they are goods, everybody's preferences go up, we should all get something of it, or at least not be punished by ending up strictly below where we were. So this is not a very demanding notion on the face of it, right? Let's make sure that if the resources to divide are better, we all are better off, at least weekly. And in exactly the same reverse context, not reverse, but alternative context. Now I think of not the resources, but the society, the number of people, not the society, I mean, I'm not doing anything macro. Of course, it's the people around the table. There is one more guest, and now we have all to share the same resource. Well, that should not be good news for any of us. There is no reason, we have the same to divide, but among more people, so we should not benefit individually. Makes good sense. And the natural question, of course, is to think, can we do that too? And of course, let's look first at the Gale-Heisenberg solution. I mean, so Gale-Heisenberg, take the Cobb-Douglas function, which is fantastic because you can compute the competitive equilibrium explicitly, right? With Cobb-Douglas, it's a simple exercise, and you will see, yes, it works perfectly. It's resource monotonic, and it's population monotonics. Everything good. Everything good. Take the linear domain, linear preferences. It works too, but this time it's not so easy to prove. It's not so easy. You have to understand well what is the structure of the efficient allocation in the linear economies. And it's tricky, but it can be done. It gives you both resource monotonicity and population monotonicity. Good. Unfortunately, you cannot go much further than that. In the general domain GE, I'm not even talking of Arrow-Debreu, I'm saying in the domain Gale-Heisenberg, these two axioms do not go well when you combine them with the previous ones. It's not that they are impossible, it's perfectly possible to satisfy them. I mean, I will give examples, but they clash with what we have been doing so far. And here I want to show you two impossibility results. In fact, I will mention two and show you one. Okay, so let's consider an axiom which is much weaker than envy-freeness. It's the axiom called no domination. It says that it shouldn't be that you have two agents such that one of them has strictly more of every good, of every commodity than the other. So that's, of course, if you have a domination like that, there is envy-free is violated because agent J envies agent I. But it's clearly a notion to eliminate such thing is much weaker than asking envy-freeness. Nevertheless, there is no division rule which is defined in the whole domain GE, which will be efficient and resource monotonic and satisfy no domination. So if I want efficiency and I want to eliminate even the most gross type of envy in the form of domination, I will have to abandon resource monotonicity. So that's so much for envy-freeness. Now, same problem with fair share. If I want Pareto optimality, fair share, and resource monotonicity, I can't. Okay? So that sounds like bad news. It is bad news in a sense, and I want to show you why. Because the proof is very simple, and the proof, not surprisingly, uses the polar opposite of the linear and Cobb-Douglas utilities, namely the Leontief utilities. The ones, Leontief utilities are the ones where the goods are perfectly complementary. So for instance, we have in this, I will show the proof on an example, but the example has everything you need. So you have 2 units of one good and 2 units of another good to distribute between 2 agents, and they both have Leontief utilities. So that means for agent 1, good A and B are perfectly complementary in the sense that 2 units of good A and 1 unit of good B are needed to do an efficient production of utility. If you miss those proportions, there will be an excess of one good which can be thrown away. So it's the standard strong complementarity idea. And so we start from this initial allocation to 2, and we assume that we have we have a solution, a division rule, which satisfies Pareto optimality, fair share, and resource monotonicity. And from these three, we will get a contradiction. Okay? All right. So the trick is we go from omega to omega star. We put 2 more units of the first good, and that means 4 of the first good and 2 of the second. And we apply fair share. We apply fair share, and here I have this U1 script of omega star. So the U1 script of omega star is my division rule. It tells me if I have to divide omega star, this is the final utility level that agent 1 will reach. So by fair share, agent 1 will get at least the utility of 1/2 of omega star. Okay? Notice that for agent 1, it is the right proportion because this is U1 of 2, 1. Right? Okay, it's the right proportion. And because of the nature of Leontief preferences, if agent 1 gets 2, 1, it means that actually his physical allocation is at least 2, 1. You cannot give him less of any good. So therefore, if he gets at least 2, 1, it means that the other agents get at most 1, 2. Sorry. He gets 2, 1. Yeah, 2, 1, because we're dividing 4, 2, right? Remember, omega star, we divide 4, 2. So at omega star, agent 2 gets at most 2, 1, right? So now I apply resource monotonicity. Agent 2 is weakly worse off when he gets omega than when he gets omega star. When he gets omega star, he gets at most U2 of 2, 1. That's monotonicity of preferences, because remember, he gets at most the allocation 2, 1. But for him, it's a bad combination that gives him only 1/2 of utility, because agent 2 is the one who needs 2 units of B to activate the utility by good, the first good. So that means U2 is at most 1/2. And now we have shown that in the initial allocation, agent 2 gets at most a utility of 1/2. By symmetry, because the model is symmetric, the example is symmetric, this is true also for agent 1. But obviously, this is what you obtain by giving them 1/2 each, which is namely 1/2 of omega, 1, 1, but you can do better by efficiency. You can give 4/3 of the first good to agent 1 and 2/3 of the second good, and symmetrically exploit the difference in preferences and give them a utility of 2/3 each, so you are not Pareto optimal. Okay? So that's tough. That's tough because it shows you that with those complementarity, I mean, unless you want to restrict attention to a special domain of utility which will include linear utilities, Cobb-Douglas, something else that I'm not able to describe. I mean, it's likely that there is a way to define some domain where those things are compatible, but totally open question. But I will have to abandon one or the other of the axioms. So this approach, still 5, 10? Yeah, no, it's good. Thank you. This approach of these solidarity properties of resource and monotonicity and population monotonicity is of course compatible with something, and the initial work, which is due to Passner and Schmeidler in the mid-70s, if I remember correctly, is to define this idea of egalitarian equivalence, which is another way, if you want, to introduce the principle of equal opportunity In the competitive solution, the fair competitive solution, the idea is it's fair because you have equal opportunities physically exposed. And now we're going to present a notion of equal opportunities which is virtual and concern your welfare. So it's different. I mean, it's not tangible. You cannot touch the goods, but here is what you say. So notice that I will define two notions, and you will see why in a second. So omega is, as usual, the bundle of goods that we are dividing, and delta is an arbitrary fixed vector, which does not depend on the omega. And you will see why it's useful. So let's look at the left definition. Find the largest parameter such that for some feasible allocation Z, we have that Zi is at least as good as a fraction lambda of the total resource omega. So what we are doing here, is an implicit or explicit, if you want, benchmark cardinalization of individual utilities. We are saying, we are dividing this bundle omega, and if I know by fair share that I should give you at least the equivalent of consuming half of that, but if I can give you the equivalent, welfare equivalent of consuming 75% of that, well, I have given you a bonus, a welfare bonus of, going from 50% to 75%. And I'm going to try to make that the same ratio, the same gain for everybody. Of course, when you solve, so I can do that either along the direction omega or along the direction delta. And here the delta will remain, a fixed arbitrary vector independently of the omega. So these two allocations, whenever you do that, it's clear that you have to be Pareto optimal. I mean, you actually go up to the Pareto frontier. You can check that easily. And they are, in fact, you could argue, if you don't like them, they are reintroducing welfarism in the sense of, cardinal utility and just ignoring what resources are, but just paying attention to your welfare. Along this neutral way, anonymous way to cardinalize your welfare. An advantage they have, easier to compute, for sure, easier to explain to somebody who is not wedded to competitive ideas. I mean, competitive notions are not that obvious to grasp the first time. Okay. Here is the thing. All right. The way I define them, both of them are efficient, and population monotonicity is very easy to check for both of them. But when it comes to those two basic properties of the fair share and the resource monotonicity, well, with those types of solution, you can have one but not the other. And we know already why you cannot do better because of these impossibilities that I showed you, this previous impossibility theorem. Namely, if I do my cardinalization along the vector of resources that I divide, then naturally I will satisfy the welfare share because I can certainly give you the welfare corresponding to 1/n of omega by giving you exactly that which is feasible. So for the egalitarian equivalent along the direction omega, fair share is a no-brainer, right? But that solution is not resource monotonic. That's the impossibility result that we discussed. And on the other hand, if I do the cardinalization along an arbitrary direction delta, then I do satisfy the resource monotonicity, but of course then I have to fail the fair share. And both of them, and both of these this solution, these rules, imply that at some profiles there will be a domination, so there will be a very strong form of envy across in the population. So okay, so that's it. That's it for today, because you know, this major solution of the CEI and the minor egalitarian equivalent are essentially what has come up in the literature as concepts which are systematically usable whenever you know that you have to divide commodities which are monotone, which are desirable, which are goods, that are infinitely divisible, right? And such that the preferences are convex. And now the next, as I said, I mean, in the next lecture, we will discuss some incentives, not too much, but some, and also discuss what happens when you remove the monotonicity assumption in these results, and which changes the whole picture a lot and brings us to some difficult open questions. So I'm glad that I did not use all of my time, because it's lunchtime, and that will make me more popular. Thank you.
Hello. Hello.
Yeah.
Is it possible to get a copy of your slides? Are they?
Oh yes, yes. In fact, I should I should send them to the send me an email. Yeah, my email is you know, the Glasgow email, and I will send them in return.
Hello.
Of course.
Hello.
It's very useful, but
Hello,
it's
hello,
useful
hello.
and fast.
Yeah.
So
Hello,
it'd be
hello,
good
hello.
to
Yeah.
keep up.
Mano, tá horroroso.
Thank you.
Absolutely.
Depois, não, amanhã. Amanhã. Não, esse aqui é para outro apresentador.
Opa, oi? Já almoçou? Não, vamos lá? Vamos. Só me dá 30 segundos. Ontem eu fiquei vendo esses prêmios novos, cheguei a 85. Impressionante. Aí eu fiz esse cara.
Tem alguma transparência aqui que...
So, Mr. Walter.
Ele não abriu a câmera. Mas manda a câmera daqui.
Good morning, Salvador. Ah, não, good afternoon, I guess. Acho que é assim.
Tá estourando, ó o botãozinho aqui, ó. Foi do botãozinho estourando aqui, ó. Pegou do Fabiano. Can you hear me?
Salvador, can you hear us?
Yes,
Okay.
yes. And now you can see me, maybe?
Yeah.
Okay, so here we are.
Yeah, you want to test the presentation to see if there is an issue?
Yes, please, because I usually am a receiver of these things, but I don't know how to download my thing or.
Okay. In your screen, there is like a share button in the bottom, like the, I guess, fifth icon.
Chat?
No, after chat, there is a share.
No, that's a problem. That I go from chat to reset.
It's a great pleasure for me to introduce Salvador Barberà, who has done significant work in many fields, in particular social choice and game theory. I have admired him from afar, and it is my regret that I haven't been able to meet him more frequently. And the regret continues today because he's only able to come online. But Salvador, take it from here. Welcome to Sao Paulo.
Thank you very much to all of you. Thank you very much to all of you and for your introduction. And yes, I also regret not being here, but I am honored to join you and grateful for your presence and for the opportunity of presenting this joint work with Anke Gerber from Hamburg University. And I must tell you that even thanks to the support team, I am able to talk to you, but I am terribly insecure in the use of this machine. So sometimes strange things can happen. Okay, but the title is Endogenous Order of Play in Sequential Games, and by myself and Anke Gerber. And let's go. So it is well understood that the order of play in sequential games in which agents cannot play simultaneously is already a restriction, may have a significant and sometimes dramatic impact on the game's equilibrium outcome. Yet it is customary in many applications to assume that the order of play is predetermined by a given protocol as modeled in the form of an extensive game. In many cases, the assumption that players will respect the protocol may be very reasonable because of institutional or natural feasibility conditions. But in other cases, the assumption may not feel very well with the applications at hand. For example, in an election, it is hard to assume that two contenders will expect the other to wait until it is their turn to take an action that can be very effective against his opponent. Or in takeover bids, it is hard to assume that the firm that wants to take over another one will wait for an opportunity to convince shareholders to sell, even if there is a protocol that establishes it, although there are some. So these are cases of applications where we think that it would be very nice to have the order of play to emerge endogenously as part of the equilibrium of the game and reflect the particular interests of those that have a chance to play at a given point. Agenda formation is a case, nomination of candidates for an office, electoral campaigns, hostile takeovers. I think we are now trying to also examine the case of matching problems, in which maybe the standard and very interesting protocols are less rigid than usually. So, because the predicted equilibrium may well depend on the order of play, we think that it is interesting to examine a situation where there is a formulation of the game and of an equilibrium notion where players' actions and the order of moves are determined simultaneously. The idea comes from work that Pascal Data, Matt Jackson, and Michel Le Breton produced already in 2004 to study equilibrium agent formation this not very well-known piece of work impressed us very much, Anke and me, and we worked on 2 papers that are published, one also relating to the introduction of issues in a parliamentary life, and the other relating to electoral campaigns. And the present paper is an attempt to preserve and present the major ideas advanced by Dr. Jackson and Le Breton years ago. But having already tested the usefulness of what they suggested as a model, trying to expand it and presenting it more generalities so that maybe they can encompass further applications that do not fit exactly with the initial assumptions, somewhat restrictive, that were used. Of course, there is a lot of literature about the idea of establishing the order of play in different formulations, but they are different formulations, mostly complicating or complementing the standard extensive form game with additional assumptions about the different ways to make a chance, for example, to affect the order of moves, or other formulations, especially in contest and duopoly games. But what we want is to push forward the ideas that we inherited from Data and his co-authors. So in that respect, we define what are, or what we call games of addition. And these are given by a number of data, a set of players, a set of actions that at some point some players or all of them may use, and sets of sequences that we call states, which correspond to histories of the play of the game with the following properties. The empty sequence is always an element of sigma, which means that we consider the possibility that the game is not played given the data. And then we concentrate on what we call states in that case, sigma, where sigmas are sequences of pairs S sub k, where S sub k tells us ik, who plays at time k, and what action this player takes, where the individual and the action, if they are in sigma, it is understood that at that time, the agent in question is endowed with this potential action. And at its sigma, there might have been potential actions for several individuals, but the idea is that at K, it was this individual who played and not any other. So that sigma in altogether can be seen as the set of histories that can span as long as the game goes, and then we're going to see when it ends. Because the game will be able to end at any point, it is important that in this formulation, each individual has a complete and transitive preference relation on each on all elements of sigma, because in this way it can evaluate whether or not it is in its own interest to stop or not. Now, in order to define, so here we don't say anything about what's going to happen, just what can happen. The notion of equilibrium then that we are going to define is based on first the consideration of what are called continuation states. At a continuation state at sigma is an element of these possible stories. One of them is not to place. Sigma is the empty set. Others are sequences in sigma. And sigma prime is a continuation of sigma if its initial segment is sigma and then follow further place after it. So a collection of sets of continuation states is a family of subsets of continuations for each sigma in capital sigma. And what we're going to do is, in order to define equilibrium, is not to consider individually the sequences, but collections of sequences which satisfy certain internal conditions of consistency with rationality assumptions. A collection of sets of continuation states is an equilibrium collection of sets of continuation states if it satisfies three conditions. And these three conditions are those that represent this notion of internal consistency and eventually individual rationality on the side of the player. The first such condition is that the continuation equilibrium collection is non-empty, and that any equilibrium continuation in the collection involves either stopping at sigma or taking some action which follows an equilibrium path from there. So as you see, this is a self-contained definition of equilibrium that includes that the continuations of a sigma are themselves also inside the set of equilibrium for the whole thing to be an equilibrium. The second condition is a stopping condition that says that a sigma is an equilibrium if and only if no player can improve by taking an action if one follows an equilibrium path from there. So if no individual wants to play any longer because its prediction of what's going to happen after that is that nothing good comes after all by following this internally self-contained object that we are going to call an equilibrium, then this state sigma will be declared an equilibrium state. And condition 3 is basically the statement that if requires a previous slide that I must skip. Oops, sorry. Before we define the third condition, which is the one that's going to embed into the notion of equilibrium that individuals act in their own self-interest, we must define the notion of what we mean by a continuation sigma prime of sigma to be rationalizable relative to sigma. So the idea is that sigma prime, which is like the first step after sigma, is rationalizable if the following conditions are satisfied. One is that the individual I, the one that is going to play after sigma, weakly prefers sigma prime over some other equilibrium continuation at sigma, is initiated by an action of some other player. That is, in a way, he says that individual I may want to act at that point because otherwise some other agent could be acting in a direction that is less favorable to him. Two, there exists no other action, A double prime, that player I itself could have been taken and that would dominate the benefits obtained from A prime because it would produce strictly better continuations by taking this A double prime. And if sigma is an equilibrium continuation itself, which means that in principle there is no need to add anything else after it on the side of I, well, then I must weakly prefer to sigma prime over sigma. That is, no gains, no losses could maybe note an additional step. So this is the idea of sigma prime being a rationalizable continuation of sigma prime. And then condition E3, we are still using the third condition to define that this overall set is an equilibrium. This condition E3, basically what it says is that if adding A prime to sigma leads to an equilibrium continuation, then that is rationalizable, then sigma prime must be an equilibrium continuation at sigma. So that rationalizability implies equilibrium continuations. That equilibrium continuations must be rationalizable on the other side. And in addition, a third condition, that if sigma is an equilibrium continuation of sigma, and there is no other player who starts an equilibrium continuation, that I must consider sigma prime at least as good as sigma. So these are the three conditions that can be definitory of what it means that a collection of continuation is an equilibrium continuation. Now, given all that, we still want to do a little bit more prediction of what may happen once we have identified what is an equilibrium set of continuations. And what we do in that respect is to start from the empty set and identify sigma star, the equilibrium states, if given an equilibrium collection of sets of continuation states, then sigma star is the continuation equilibrium of the empty sets. So in that sense, not only the equilibrium tells you about the the final result or results, depending on whether you have uniqueness or not, but also tells us what is the actual path that among those that we started defining as equilibrium will actually be taken and satisfy all these conditions. Well, after all, in our papers, preceding papers, this relatively involved notion of equilibrium becomes manageable because it involves, again, a form of induction. So the next step in my presentation is to explain a few examples which are extremely simple, maybe a little bit too simple, but we find educational because what is their intention? The intention is to prove that you can get uniqueness, and then you'll identify later on some conditions under which you can get uniqueness in spite of the kind of complex structure of the notion of equilibrium. Other cases where we get only one possible equilibrium set of continuations that allow for several different equilibrium outcomes. Another example in which we are going to explain that in fact there is only one equilibrium action for a given set of continuation equilibria, but there is another set of continuation equilibria which provide a different answer. And finally, we'll also have to allow or admit that unfortunately there may be situations in which our definition does not lead to an equilibrium, which is something that is unpleasant always, but that has honorable company because many well understood and appreciated equilibrium notions also suffer from this, and this is maybe the price to pay for a paper that wants to generalize without further assumptions the ideas of others who were lucky enough, including us, to produce examples or applications where existence was guaranteed. So here are the simplest examples that you can imagine. 2 players, blue and red, 1 and 2. Each player has only one action that can only be taken. So actually there are only 4 states, A, B, AB, and BA. The first example is one in which there exists a unique equilibrium state. And the idea is that the continuation of A is in B, which follows from the fact that player 2 prefers A B over A. And the continuation of B is B because player one prefers player player one prefers B to BA, therefore player two, if it takes this action, will get stuck at B. Our initial assumption is that it's always, in principle, the continuation of possible continuation of the empty set is the continuation empty. So we have we are left with empty and AB and B. But since player one plays AB, prefers AB over the empty set, the empty set is not an equilibrium continuation of itself, because there will be movement toward AB. And if AB is a continuation of the empty set, then B is not rationalizable, because 2, which would be the one to take the action leading to B, which we already said was a final state, in case it was taken, then is someone who also prefers AB than B. So at the end, the AB continuation of the empty set of B violates B3 because it's not rationalizable. Therefore, this is the equilibrium collection. Maybe I overdid in explaining in detail this thing that looks almost like a essential form game in terms of this description of what's going on. But it's just to emphasize that the reasoning here is maybe a little bit more involved, because it involves also the statement that the state that constitutes both the equilibrium, the set of equilibrium states, and the state itself is the state AB. Second example. Oops. Sorry. Okay. Multiple equilibrium states. In this example, nobody likes the empty set, and one refers A, which is the action that we can take, and B prefers. The second guy prefers B, which is the action that he's entitled to. So it's a typical case where both are in a hurry to play first. And this is what is going to happen if we call also that's what comes out from our analysis. The continuation of A is A, the continuation of B is B. So these are the starting points eventually, because AB is not rationalizable, because BA is not rationalizable. So the potential elements for an equilibrium set is the empty set, or the singleton A, or the singleton B. But the condition of 2, doing better if possible, establishes that the empty set cannot be part of this equilibrium set. So eventually, But on the contrary, the set A being among the being part of the equilibrium set is can be rationalizable, and similarly, A is rationalizable if B is. No. So there are two equilibrium collections here. A is an equilibrium collection, which corresponds to a case where A plays first and nothing else. B is an equilibrium collection. That's all there is. A little bit similar but different is the analysis of a third case in which where there are like two equilibrium connections and each one of them is associated to one outcome. Here is a different case because now this is the case where both individuals prefer actions that can be taken but over the empty set, but one prefers the action that two can take, whereas two prefers the action that A can take. And therefore, in this case, the continuation of A is A, the continuation of B is B, because both actions are really bad and work on the empty set. But if A is the continuation of the empty set, then B is not rationalizable because player 2 prefers A over B. And so the continuation of the empty set is A, and similarly with B, the continuation of the empty set, then A is not rationalizable, and it implies that the continuation of the empty set is B. So there are two equilibrium collections. In one, the continuation of the empty set is A, and another one, the continuation of the empty set equilibrium continuation is B. And so the outcomes are A and B, but they are supported by different assumptions in that preceding case. The third and last example is this example with no equilibrium, where there is a case in which we are going to claim that there is no equilibrium because there is a conflict between the rationalizability of two apparently reasonable outcomes or justifiable, but cannot be justified at the same time. So, for example, the continuation of A is A again, and the continuation of B is B. So the family of continuations at most will be composed by the empty set and by the singletons A and the singleton B. And you see, this is a situation where one has no reason to move, apparently, except that if player 2 was to play what he's allowed to be, he would go worse than what he is now, which is not to play. But on the other hand, there is no reason why player one would play unless it was to preempt the danger that two would move. But two, on the other hand, refers one to play and preempt his action B, which would be the one that he has available. And well, at the end, a complete analysis of the situation leads us to a situation in which we cannot rationalize A without rationalizing B, but none of the two is rationalizable separately, and their joint rationalizability would contradict the fact that one of them is not going to move in his favor. And that creates a conflict that we have not been able to eliminate, at least in our understanding of the solution concept, which is troublesome. But on the other hand, as I said, bothers us. We could have tried to maybe reduce a little bit the demands of rationalizability, but that would create other problems. So at the end, we are trying to live with the idea that, as in many other cases, one needs to make certain assumptions about whether or not the application that one has in hand eliminates this possible danger of non-existence, which in fact was the case in our previous work. So because of this, and also for other reasons, we started, in addition to produce this general framework, to study special cases for two reasons. One, because to understand why we didn't get in trouble in our previous work, in which there was always existence, and in certain cases uniqueness. And second, because this exercise that I am doing in front of you is an attempt to recruit people who, like us, has some hope that these ideas of analyzing more globally sets of internally consistent actions could lead to improvements in our predictions regarding outcomes when the order is not pre-established. And so that's why we try to produce certain theorems that would address special cases that coincide in this case, because our imagination was limited, with the kind of examples that we had dealt in previous papers, but that I think are also of certain general interest and value. One of them is the following result of existence for games in common action sets. For example, in the case of two of the papers, one of ours, one of Pastor Gatos and friends, the action sets available to different individuals were the same. For example, putting in an agenda setting context, proposing some issue to be introduced in the agenda is something that anyone could do in our models. And once done, there was no point on anyone else putting again in the agenda because the point was already in the agenda. So putting individuals or agents or issues in an agenda was one of these cases of common actions. And under these conditions, and in addition, the player's preferences over sets only depend on the sequence of actions that have been taken, but not on the identity of the players who have taken the actions. Then we could prove that in this context, there exists an equilibrium collection of sets of continuation states. As you see, in an existence example, there was one where individuals would not have the same actions. Another case for existence, very classical, two-player zero-sum games. Well, in this context, we have always worked with ordinal preferences. But the idea is if we have preferences such that if one of the agents refers sigma to sigma prime, then necessarily the other agent refers sigma prime to sigma, and we restrict ourselves to two agents, then again we can prove that an equilibrium collection of sets of continuation states exists. Moreover, and finally, there is a special case where, under appropriate circumstances, we can guarantee order independent preferences, and that order we can guarantee uniqueness of equilibrium if there exists situations, it's a condition on the preferences of agents, that what matters is not the order in which different actions have been taken, but as long as the actions taken at the end of the game are the same in one case and in another, then the payoffs for individuals are not affected by the order in which these actions were taken. And if that is the situation, and in addition to being zero-sum, with already guaranteed existence, this property of order independence holds, then all equilibrium collections of sets of continuation states are outcome equivalent. Okay, this is what I have in my slides. I also have to mention that we thought I have more restricted time, and that I should introduce what is already in sitting papers, that it is okay. You could ask, and so what? I mean, are we going to get the same results by using this methodology than by appropriately modeling the extensive form games? To make a fair comparison, and given that in our case we allow always for a game to stop at any point, we compared the examples that we had with examples of extensive form games in which we included at each stage the possibility that individuals do not take an action and pass the benefits that and even under these approximating similarities, we have examples in which we don't get the same predictions of fertility. Okay, I think that we try to open then, in summary, the amplitude of these initial ideas. There are many, many things to do. All this is subject to the strong assumptions of a lot of mutual knowledge. It's initial assumptions that there is no simultaneity is possible. So of course there are applications that this cannot be used, but we kind of wanted to offer these ideas for competent people to adapt to them and maybe expect better results. And at the same time, we are also hoping in our own strengths to at least find new applications. That's it. Thank you. The questions, comments. Of course, I will definitely appreciate.
Any questions? Okay, well, then once again, we thank you very much. Wish you could have been here in person.
Thank you. Thank you very much. Thank you very much.
Ready.
Okay.
Okay. So it's my pleasure, my big pleasure to chair the session of Pradeep. As you know, he's an expert in many different areas in game theory, including cooperative game theory, which has given a course about strategy, market games, etc. So, you know, welcome him. Thank you.
Can you hear me? Okay. So this is joint work with Siddharth, and that's the theorem, that the main theorem of the paper. So I will make it precise, but the idea is that if many parties are contending several elections, as they do in many countries, right? Elections at the center, at the state level, and if the electorate is polarized, which is also happening both in USA and India. That means people have decided in advance which party they will vote for. There is no undecided voters. Then the only uncertainty left in the election is the turnout. Who will turn out to vote? And that's the focus of this paper. And under certain assumptions, which I'll make clear, we prove that if elections are held simultaneously, then the probability that a single party will win all the elections goes up. This is when the single party wins all the elections, we call it a single party sweep. So it goes up for every party, as opposed to elections which are held at different years or different months. Okay, and this will be proved under certain assumptions, which I will soon make clear. But, at the same time, held at the same time instead of at different times. So I have to now show you why. Different elections. Okay. So, sorry. All right. I'm going to give several examples, but maybe before I turn to elections, let me mention one thing. There is something well known called the Harris inequality, which is in probability and combinatorics. It's very useful, and it's been used to study random graphs, percolation, and so on. I want to show the connection of our paper with this. So let me do that first and then turn to elections. So the inequality is as follows. Consider a finite set and the lattice of all subsets of that set, partially ordered by set inclusion. Okay? And now consider two functions on this lattice, real valued and increasing, weakly increasing. So if a set, you know what weakly increasing means. With respect to set inclusion, with respect to the partial order, right? And then let's consider what is called a Bernoulli probability distribution on the lattice, obtained as follows. I've written it. Each element is in with probability P and out with probability 1 minus P. The P can differ from element to element. This defines the probability distribution on the lattice. I think it's called the Bernoulli probability distribution. So their famous theorem is that the product, the expectation of the product is bigger than or equal to the product of the expectations. Okay, that's a well-known theorem and much used in, we have in the course of our analysis, we have a slight generalization of this theorem, which I will state. And let me define the following notion. We say that a function is defined on the lattice, a real valued function, is increasing at h if the marginal contribution of h is non-negative for all s. Okay? And if it's less than or equal to, say, we say it's decreasing. So now we say a family of functions is aligned if for each H, its marginal contribution is in the same direction for all the functions. It could be high up for some H and down for other H. But for all functions, it will be the same. So notice, the elements that are helpful and elements that are hurtful. Okay, but both kinds of elements could exist. Now, notice that if all the functions are increasing, they are clearly aligned. But aligned is a slightly more general concept. Basically, the Harris inequality is true if the functions are aligned. They don't have to be increasing. That's a consequence of, we arrive at that in the course of our analysis. That was not our aim. And we arrive at it for purely game theoretic considerations. So let me now turn to elections and you'll see how. So I've set this page. Yeah. I said they are non-negative functions. Non-negative functions. Yeah. I said that, or at least I wrote it. Yes. For every or M plus F1 and M plus F2 are. No. Okay, if you add a constant, they remain aligned, whether it's negative or positive. Yeah, okay, so I'm glad it's not obvious. Okay, all right, but let me now turn to elections. That was an aside, but I thought it's important to mention. Let me turn to elections and all our assumptions. So I'll first describe a situation of voting among shareholders. So there are two companies, A and B, and HA is the set of shareholders of company A, HB the set of shareholders of company B. There are some people in the intersection, they hold shares in both companies. Okay, they have to they have to all vote on some joint decision J. Now, I'll assume that the shareholders are polarized. So we have a partition of all the shareholders. Each person either favors J or is against J. Okay, so that's a big assumption, polarization. An even bigger assumption is that each person. So now, if there is a vote, it will only depend on who turns up to vote, because once they come, they'll vote according to the polarization. In our context, there is no reason for people to vote other than truthfully. Okay, so I'll just assume they vote truthfully. Even if they could vote strategically, they'll still vote truthfully. We'll see that. Right now, I'll make it as an assumption. They are not ranking alternatives. They are just choosing one best alternative. It's what I think Eric Baskin called bullet voting. Okay. Now, I'm going to assume that the voters are polarized. Either they are for J or oppose J. The bigger assumption is that each person, the turnout uncertainty is idiosyncratic. Each person H shows up to vote with probability PH independent of the others. Okay, that's a big assumption. Restrictive. It's also it's an assumption that both Penrose and Bunz have made, Lionel Penrose and Bunz, in the context of voting, but undoubtedly it's restrictive. Okay, but we are going to maintain this assumption. Still, there is something to be figured out. Now, this is a $1 one vote situation. So a shareholder has he has as many votes as shares. So I'm going to make that assumption. Now, how we can imagine the election running in many different ways. Number one, I'll just say them in words. One, there is an election in company A and another election in company B. In company A, you look at all the people who turn up to vote, and if the numbers who vote for J exceeds those who vote against J, the J wins. Okay, and that's the case in each company. Remember, the number of votes a person casts is proportional to his shares. So that's one way to decide. Two, you can put a twist on it and say, we'll look at all those who voted for J, but it better not be too small. It should cross some prescribed threshold, then it'll win. Otherwise, we'll say it loses. Third, a third way is to say that that those who don't want to vote in favor don't have to show up. Only those who want to vote in favor show up if they form a winning coalition in the company. So you see, you add up all their votes. If it exceeds a quota, they win. That's one way. But more generally, we can imagine a simple game, a voting game, defined by declaring winning coalitions in each company. If the set of people who show up to vote form a winning coalition, the issue passes. Otherwise, it fails. That's a third way. And there are other ways of defining elections. Our notion of how the turnout maps into a victory will be very general, and it will cover all these cases. So now I'm going to repeat for you that the difference between holding them on different months or at the same time. If elections are held at the same date, this picture might help. If Mr. H arrives in the room, there are two booths, one for casting votes in company A and the other in company B. If he is a shareholder of both and he arrives, he'll cast his vote in both, right? And if they are held on different dates, this is held in 1 year, this is held many months later, then a person who is in both will arrive here with probability PH, and again over here independently with probability PH, and if he arrives, he'll vote the way he wants. Is that clear? Okay. So here I claim that the probability that the joint decision will be taken, which it will only be taken if it's voted for in both companies, is higher when the elections are held simultaneously rather than on different dates. That's an example. You can have many alternative joint, by the way, it's also the probability that the issue fails to be passed in both places also goes up. Both go up. What doesn't go up is a mixed decision. Okay, that's. By the way, you could have several joint decisions, one of which have to be taken, and the same theorem will hold. So we can think of J as a candidate or a party, not J as another party. They are contending this election, two separate elections. I'm now turning to more political elections. It has been observed empirically that a single party wins multiple elections with a higher frequency when they are held simultaneously. And in America, this phenomenon, there's a word called the coattail effect, which basically says that, so in America, there are elections to the Congress, which is the House of Representatives, and the Senate. And there is also the presidential election. Elections to the Congress, which are held at the same time as the presidential election, one party is more likely to win both if the presidential candidate is popular. And this is described as a coattail because members of Congress are voted into office hanging onto the coattails of the popular president. So this is something which political scientists talk about. Similar phenomenon has been observed in India. So there are two kinds of elections in India, for the central parliament called Lok Sabha and for each state called Vidhan Sabha. And so it has been just observed in the data that Vidhan Sabha elections that are concurrent with the Lok Sabha, the center elections, state elections that are concurrent with the center elections have a higher probability of one party winning both. This is just in the data. I'm not making it up, okay? And various explanations have been given, which are all probably right. One is that a popular presidential candidate can mobilize each person in his party base to turn out to vote with higher probability. That's one thing. Second, he can sway undecided voters to his party's fold. Okay, so these are things which will help his party to win the Congress elections. These are, a third could be an anti-incumbency factor. Once a party is in power and has made tall promises which turned out not to have been fulfilled 3 years late, 2 years by the midterm, then people turn against it. So these are some explanations. All these aforesaid causes are missing in our model because we have fixed for each voter. There are no undecided voters because we say it's polarized. Each person, if he shows up, we know which party he will vote for. Second, the probability of his turnout is fixed. It is not susceptible to influence. So all these causes are not in our model, yet the same phenomenon is true. So we are trying to unearth the boosting of sweeps for just based on the statistics of voting. And if these other factors were brought in, we don't go against it. They could be included in our model. If a president, increases the probability that his voters will turn out, it'll accentuate the sweep even more. Okay, so I'll go back to India later, but let me now start stating things a bit precisely. So think of two countries. We are going to look at country A, country B, country C, and describe the elections in increasing generality. Country A, there are two elections. One is presidential, the other is parliamentary. In the presidential election, there are two political parties. Whichever party gets more votes over here will win the presidential election. Here it's different. The country is divided into electoral districts, and in each district, whichever party gets more votes, a candidate will be elected from that party. And you now look at all the candidates across these districts. Whichever party gets more candidates elected wins that election. Now it's clear that a party can win the first and lose the second. Okay, so they are not completely correlated. Yet it is true here that if you hold these two elections on the same date, the probability that that party 1 will win both goes up compared to when you hold them separately. Party 2 also will win both with a higher probability than if you hold them separately. So if you hold them separately, what goes up is that it will be a mixed result. Okay. Country B, I'm saying there is a finite set of voters and a finite set of elections. And as before, the electorate is polarized into, disjoint sets. And then the polarized, well, I didn't give a symbol for parties, but everybody has decided which party to vote for. And if people have decided to abstain, you can forget about them. And then you run the election, the same result is true. And I now want to describe how we decide victory. So, turnout. I want to define turnout. So a turnout in the N elections is just a set of pairs. We say a person H and an election L, we call it a turnout if Mr. H turns out to vote in election L, okay? So we have the notion of turnout. And given a turnout, I want to describe the notion of a win. So let me be very simple. For any turnout in an election, Okay, so now I'm looking at turnouts on all elections, which is made up of turnouts in each election. So I say the turnout, let's say that the outcome is some party wins. Huh? If it's a tie, we could toss a coin and say each wins with probability half. So the outcome of a turnout in an election could be, in generality, probability of each party winning. But I want to suppress all that. And I'll say, given a turnout in an election, we know at most one party can win. Even that is not required mathematically, but you will assign which party wins, okay? And here is the only assumption we are making on how victory is defined. And the assumption is, given a turnout, if an additional vote happens for a party, T, it can't hurt that party, nor can it help its rivals. So that's the only assumption I'm making on the electoral rule. Nothing else. So first past the post, which is in India and USA, or proportional representation, everything fulfills this. Okay. The only time it doesn't work is when the outcome depends on your ranking of parties, with more than one in the ranking. Then this can fail. So I'm not looking at border rule or any other thing, just bullet voting and a very general class of elections. Okay, so now I was describing India here. It's worth mentioning. So there are elections for the center, where the whole country is divided into large electoral districts, and 540 actually. And in each district, many parties fight the election. Whichever party gets the maximum number of votes wins, that elects a member. So we look at members elected all across India, and the party that has most members forms the government. It may be that they have to cross a certain threshold. And here is one state, and these are elections for that state, smaller districts. Again, first past the post. So a similar thing happens in USA. Okay. Now, let me now formalize. A polling schedule is a partition of the election into sets of elections that are simultaneous, that is held on a common date. So I say one schedule is coarser than another if it's more simultaneous. Any two things which are simultaneous, the red schedule is coarser than the blue if any two elections which are simultaneous in blue are also simultaneous in red. It's just a coarsening of the partition. Theorem, a coarser polling schedule has a higher likelihood of a sweep. Country C. We now define something called staggered schedule. In India especially, you can't hold an election on the same date. It's too big. So a single election is held over a period of time in different parts of the population. There's just not enough machinery to conduct even one election everywhere at the same time. So I want to describe a staggered schedule in which each election might be spread out over several dates with different poll dates for different regions. And abstractly, since a region may consist of just one person, we'll say a staggered schedule is a collection of partitions, one for each person, over the set of elections in which he has to vote, okay? Many of them could have the same partition. Okay, so now I say a staggered schedule is coarser than another if for each person it is coarser. That's all. Now I think I can state the result that a coarser staggered schedule has a higher likelihood of a sweep. So I'm going to try to prove that result. By the way, it also holds if there are alliances. Trivially, if some parties get together before the elections and they decide to fight jointly, that is, they won't fight each other, then you can treat it as one party. There's also the concept of a post-poll election. The parties in the alliance fight against each other in the election, but then they join, the elected candidates join after election. Both kinds of alliances, our theorem will still be true. If you think of the alliance as one party, it'll break when the alliance depends upon the turnout, or it varies from on the election schedule. Here I have to assume that they have decided in advance how they will get together after the elections are over. If that alliance depends upon the turnout, then our theory won't work. So it works even with political alliances. So now if there are any questions as to what I'm trying to prove, I should stop. But if it's clear what the theorem is, then I'll give the proof. Okay? Yeah. Okay. Real life. Okay. Yes. Yes. Okay. It won't apply. Yes. Yes. Huh. Huh.
What happened was that when people voted strategically for the prime minister, namely everybody on the left voted for the big left party, everybody on the right voted for the big right party, and in parliament they voted for the small party that was aligned to what they wanted.
I see.
Whereas when you only voted for the parliament, there was a lot of strategic voting, so the big parties were getting much more of the vote.
Okay.
So what happened after 2 or 3 such elections, the big party from left and right go together, decided we are losing votes. So they canceled that. We are back to the old system.
Okay.
That's exactly an instance where having 2 elections at the same time allows you to vote in those 2 elections differently. As a consequence, makes me less likely.
Okay. Yeah.
Yeah,
you will figure that out. But I understand. We are proving a theorem with certain assumptions, and I realize they don't have to hold all the time everywhere. When they hold, we have something to say. Yeah. All right. Huh? Yeah. However, the data does show what I said. Okay, simultaneous elections, one party winning, more likely to win, winning with higher frequency in the data is true. For India, at least, there are some papers on it, and also in the US. Okay, now I can try to give a proof. I have stated the theorem. I can try to give a proof, and the proof is really, I don't know how much time I have left. 20 minutes. The proof, first let me tell you, is extremely simple. I think we only need to know how to add and multiply numbers, nothing else. There's no mathematics here. So let me try to give the proof. Okay, and it does generalize Harris's theorem in an interesting way. So let me try to give the proof. So we are going to look at the election schedule for each person. We are allowing it to vary from person to person. Okay. So for Mr. H, I'm indicating his election schedule. It's one set, MH1, MH2. The order doesn't matter. He has to vote on separate dates for these group, for that bunch of elections. That's for Mr. H. All right. And we can then define, once we have a partition for each person, we can define a probability distribution on turnouts. Okay, because each person will show up to vote in any set with probability PH and not show up to vote with probability 1 minus PH. Therefore, if you look at turnouts, what is a turnout? Pairs of a person, election is in the turnout if he turned out to vote. So we now have turnouts, and on turnouts we have a probability distribution. Many turnouts will have 0 probability distribution. Will have 0 probability. Okay, so here is a picture. there are 4 elections, alpha, beta, delta, gamma. There are many people, A, B, C, D, E, F, G, H, and this is telling me, this picture, that Mr. A voted in elections alpha, beta, and delta, and so on. So that's a turnout. Given a turnout, by the way, this turnout is not consistent. If Mr. Beta's election schedule was here, like this, it had to mean that he either showed up in both alpha and gamma or in neither. If you look at Mr. B, he's showing up in alpha but not in gamma. So this turnout would not occur. We'd have 0 probability if this was the election schedule of Mr. B. So I hope you understand how I generate a probability distribution on all such arrangement of dots. Okay? Huh? Yeah, alpha and gamma should either both be there for Mr. B or not, both should not be there for Mr. B. But this violates that. So, yeah, okay. So I don't know what you were saying, but maybe, okay. All right, so now, given an election schedule for each voter, we have a probability distribution on all possible turnouts, okay? That's very clear. Also, by the way, a turnout is defined completely by the turnout in each election, okay? It's made up of turnouts in each election. So if you look horizontally, you're getting out the turnout in elections, and the two are sort of one-to-one. And now we have a win function, right? For each election, we can compute whether there was which party won. Yes, we have these abstract win functions. I don't care whether they come from first past the vote or proportional voting or something else. Any function which satisfies that condition, that if a person if a party gets an additional vote, it can't hurt the party and it can't help its rival. That's all. Okay. So now I can compute the probability of a sweep as a product here that I have described. And I have to show that this probability goes up for every party if you coarsen the partitions. If you go to a coarser staggered schedule, that's all I have to prove, right? To prove the whole theorem, because okay, so I'm going to now prove this. And I have already defined increasing, decreasing, and aligned. And so I'm going to assume that these functions, these win functions, they are clearly aligned. I first observed that, because if you look at one party, fix a party, and look at its win in all the elections, they will all be increasing if the voter is in favor, and they'll all be decreasing if the voter is against. So the win functions of a given party across all elections are aligned. That's very clear. Okay, so given that, I'll now prove what I want to prove for something more general than 0-1 functions, arbitrary real valued functions. Okay, it will imply it for the 0-1 functions, which are our election functions. And I'm going to prove this for functions which are non-negative. I forgot to put the R plus there. In the first line, it should be R mapping into R plus. Okay. I'm going to prove this for not just 0-1 valued functions, but all functions. And I have to prove this. And so let me just go and prove it. I think it's easier to show you the proof. Here is how we'll prove it. We will take one person and we will say, let him just coarsen a bit of his partition. He has the partition pi prime. Let me coarsen it to pi by him joining just 2 pieces. And if I can show, and the other partitions are fixed, if I can show that this action will improve the probability of a sweep for every party, I'm done. Okay. So now we are going to do something totally crazy. I'm going to imagine a game which is never played. I'm going to imagine a game in which each player picks his own schedule for voting, his own partition. Okay? And so in a game, I must define payoffs. Well, I'll define the payoff in this game to be the sweep for a party. I choose a party in advance. And I'm going to show that it's a dominant strategy for this player to pick the coarsest partition. So it comes from game theory. If I prove this for the totally fictitious game, I'd have proved the theorem. Actually, this is how we came to the theorem. So how do we prove it? Well, I will imagine, let me tell you the idea. I'll prove something a little stronger. It's not just dominant. Dominant means that a guy's expected, the expected probability of winning, sweeping for his party goes up. I'll show something more. I'll show that conditional on any turnout of the others, conditional ex post optimality, conditional on any turnout of the others, his payoff goes up if he switches from pi 1 to pi prime. So this is more than dominant. I'll call it ex post dominant. And so it's easier to prove the stronger result than what we need. And so here is the proof, rather simple actually. We will imagine that all others, including himself, so he is also split into people. M1, M2, M3, all the others have voted. He has also voted on all the elections except the 2 that he's joining. Okay, so his own turnout on the rest of the elections is fixed. Others' turnout on all the elections is fixed arbitrarily. Okay, remember he's choosing independently. And now I say we are going to compare if he tosses the coin once and goes to vote in both M1 and M2, or if he tosses once, goes to M1, he tosses a second time, it goes to M2. Okay, that's the only comparison I'm going to do and show that it's better for him to toss one coin for both. And then, okay, so we have even said his own turnout in M3 to MK is fixed. Others' turnouts everywhere is fixed. Conditional on that outcome, he's going to do better by a single coin toss. All right. So I don't know, maybe this is getting too much, but we simply look at his effect on the payoff. I define AI, BI, and C this way, and the probability and his payoff, if you look at it this way, turns out to be A if he does a single coin toss, and B if he does 2 coin tosses, and where others actions and their effect on the sweep is fixed. And we just show this by pure magic. It looks as if we have to prove that the function of 2 variables, x comma y equals x times y, should be convex. That's what it looks. If we could prove that, we'd be done. But the function of 2 variables, x comma y, defined by x multiplied by y, is neither concave nor convex. If you go, if you go from, what's this direction? If you go towards on a ray going northwest, it's convex. If you go on a ray going northeast, it's convex, and northwest, it's concave. This function is neither concave nor convex. And so that kind of thinking won't help you. You have to do a hard calculation. And the calculation is just what I did here, that A minus B factors out like that. To me, that's the only math here. The rest, I did nothing. I just took the concepts and kept translating them. I just did nothing at all. I just unraveled the meaning of a sweep and how a guy votes. Okay, and I arrived at this simple thing, and the fact that A minus B factors this way, I'm calling it magic because I can't explain why it factors. But once it does, it's clear that it's non-negative by alignment. Either both A1 minus B1 and A2 minus B2 will be negative, or both will be positive. That comes from alignment. Okay, and that's the proof of the theorem. So I realize painfully that I have made a lot of assumptions which are not true in practice, Sergio. First of all, it's not true that people vote, their probability of turning out is independent of each other. That's a huge assumption. All right, by the way, if one guy inspires others and takes them along, you can treat him as one person with many votes. So that's easy to accommodate. But this is a strong assumption. I don't know how far we can extend the conclusion under broader assumptions. But even with this assumption, it took us some work to show what we showed. Any questions? Okay. I hope I finished early. Okay.
Thank you very much.
I have no more to say.
Hi. If voting was costly and the P was endogenous, the turnout rate, so would it be the same in when you're computing A and B? And right.
Don't know the answer to your question. It doesn't fit into our model. Yeah. It does not fit into our model. You could have asked another question, which I'll ask. If there are, yeah. You could ask that if there is a lot of people and so on, the law of large numbers makes this theorem irrelevant. It doesn't matter what schedule you do. But I'll tell you where it is relevant. If, think of two parties, India, BJP, and the allied opposition. If lots of people are committed to going, and only a smaller number is undecided about showing up, then this effect will be strong. In the case of small elections like the shareholders, it will always be strong. Okay? But of course, if it depends on the polarization. If a lot of people are surely going to vote for BJP with high probability, then why hold the election? It doesn't matter what the schedule is. So I'm agreeing that the effect, it will always be positive. A sweep will have a higher probability than separate elections. How much higher depends on the data. Okay.
Just one point. But related to that, is there a theoretical justification for a P, an exogenous P that is not 0 and not 1?
Yeah. Okay. Well, there have been studies of looking at voting as strategic games, and then mixed strategy equilibria come into existence, where each person votes or not votes with the probability. So there is that little bit of foundation for independent decisions. But I'm not convinced by those models either.
Any additional question?
Yeah.
It's been a while since I read Shugart and Carey's book on presidential democracy from the early 90s, but when they were looking at the history then, I haven't followed it since. The stylized fact was that in presidential democracies, independent voters tend to prefer divided government, so that by having the Congress elected after the presidential election, you're much more likely to get the majority against. Once everyone knows who's won the presidential election, then they vote for the other party to get divided government. Independent voters vote for the other party, and that's a pretty strong pattern in American politics. Obviously, we have simultaneous elections and then the midterm elections in the United States, and the president's party usually loses votes, so that's another reason why simultaneous is better increases the probability of sweeps for better or for worse.
Right. So what we are saying is even
not 2 years later, which makes a big difference. I'm not sure the results are the same. Again,
my recollection is Shugart and Carey were talking also about having the 1 month separation in there itself. That also helped. But you're right. 2 years later, people are fired up about what they don't like about the president, and people who like the president are less fired up. But a month later already, they know.
So
don't want to give him too much power.
Roger, if I may just respond to what you said. We are saying that even if Yeah, so holding them separately will increase the chances of division. Yeah, it's not sort of, it's in the same direction as yours, but for independent reasons. Just based on counting votes. Okay. Any other? Okay.
So thank you very much again.
Pleasure.
the product of quality score and the bid. And then the top score bidder, whoever has the higher score, is going to get the top slot, and they will pay their bid when they get a click. And the second score bidder is going to get the second slot, right, and pays its bid if they get a click. Okay? So what are the expected payouts? Well, the top bidder is going to get, suppose the top bidder is I, she's going to get few I clicks, and then from each one of those clicks, the profit is just 1 minus the bid. Okay, it's really straightforward. Everything here is really straightforward. The second bidder is expected to receive alpha times their score, right? Because 1 minus alpha fraction of the users don't even scroll down to the second position, right? That's why everyone wants to be in the top position rather than the second one. And again, gets 1 minus his bid per click. Okay, so that's the game. And here is theorem 1, which I'm not going to go through the proof because the proof is just basically elementary algebra. There's nothing very insightful about it. I will show you some intuition afterward, but the proof itself is not very interesting. You set up the game and you find that in this auction, there exists a unique symmetric pure strategy equilibrium. Here is the formula for this equilibrium, and everything is uniform. So we get nice clean formula, just as a sanity check, right? If you put alpha equal to 1, so the second slot is as good as the first one, you get 0 bids, right? Because there's no reason to bid for the top slot if they're equal. Okay? And if on the other hand we have one position on the screen, right? So alpha is equal to 0, then everyone bids half of their value, which comes from linearity, standard, inverse parabola. Okay. So what's the intuition? What's going on? And I'm going to show you some more pictures that will drill this intuition even further, even more strongly. Well, so what's going on here is when you were in the old world, where you knew that all you have to do is to outbid the other advertiser by a penny, and you can actually do that. So you have this very sharply discontinued pair function. Once you introduce uncertainty, the function gets smoothed out. Okay, so instead of having this very precise best response where pairs are very discontinuous, they get more continuous. Now that's not enough actually. That's not enough because even with these smoothed out pairs, at least you have like differentiable pairs and you have a candidate best response, but you still need to check, and I'll show you when this result, I'll show you how to bring this result in a moment. You still need to check that when the bidders bid at this candidate equilibrium, they're better off than just by bidding 0 and getting the lower position for free. Okay? All right, so that's, I'll come back to that. But for now, let's do something that we actually can do. So remember, this is the formula, right? 2 times 1 minus alpha over 4 minus alpha, nothing complicated. So this is the part that surprised us. We're like, wait, that's surprising. Revenue comparison, GFP versus GSP. Okay? So first, we need to figure out what the equilibrium is going to be in the generalized second price auction. Okay? And in this particular setting, it's actually very simple, right? Because the way to think about the second price auction and the setting is there are 2 bidders, 2 slots, so you know that you're getting the bottom slot for free, right? So all the competition is for 1 minus alpha of the visibility, okay? And by the standard argument, here they need to be adjusted a little bit because they have quality scores, but they turn out not to matter because they multiply on both sides of costing the benefit. You just bid your value for those extra clicks. Okay, so in the second price auction, the bid is just 1 minus alpha. Okay, with this we can do the revenues. So at the top we have revenues in the generalized first price auction. At the bottom we have revenues for the generalized second price auction. So let's see where these things come from. So you, in both expressions, the first term is just the optimal, it's just the bid, the equilibrium bid.
right? So 2 times 1 minus alpha over 4 minus alpha. Here it's 1 minus alpha, okay? And then at the top, this alpha plus 2 over 3 is just the expected quality score, right? So if with this bid, right, the higher quality score, which an expectation is 2/3, you're going to get 2/3 of a click, and the lower quality, which an expectation is 1/3, because we're drawing it from the uniform distribution from 0 to 1, is going to get alpha times that, so you have alpha over 3. Okay, so that's the top, that's the revenue for price. At the bottom here, right, it's basically what you're paying for is, at the bid of the second highest bidder, the total sort of bid times their applicability, times their quality score, so their expected quality score is 1/3, so that's the expected payment in the second price option. Okay? And you stare at these two expressions on the right. I mean, the first thing you see that they're not the same, which is already kind of interesting. I'll come back to this in a moment. But then you also, lots of things will cancel out if you divide top by the bottom, right? 1 minus alpha is going to cancel out, 3 is going to cancel out. And so what you're left with, once you cancel them out, is that revenue in its first price option. In this very simple example, okay, just sort of caveat, we also have an example where it goes the other way around. But at least in this simplest imaginable example, you get that the ratio of the revenues is 4 plus 2 alpha over 4 minus alpha. And if you plug in this typical value of alpha of 0.7, which empirically how things behave, we have the ratio of the revenues of about 1.6. Okay? So this was all mechanical. But then this is an auction theory question. For those of you thinking the auction theory, how can this be? So everything is symmetric here. Okay? I have an answer on the next slide. Everything is symmetric here, and allocations are efficient, right? So whoever has the higher quality score is going to get the object. The values, everything is independent. So we have an independent private value setup with identical allocations. It's too bad the Roger is not there, but I would Paul. I know Paul knows the answer. So how can it be? Okay, actually, you know what? I'm going to ask volunteer. Why are they not the same? Going with volunteer. Sure. Yeah. So that's exactly right. But it's kind of neat that we didn't cook up this counter example, right? This is something that sort of jumped at us afterward. So what happens is, remember that revenue equivalence is only true up to the payoff of the lowest type. And here we don't have type. We do have type, but the type just has 0.1. So the revenue equivalence theorem says absolutely nothing about the payoff of the lowest possible type, which in this case is the only type. Okay? Now in the paper we actually go, I mean that's sort of a technical answer, but in the paper we actually go through, we really wanted to understand what's going on, and the way we actually did it in the paper was like, wait a second, let's fix the behavior of one of the players. For the other one, let's actually assume that their type can be all the way from 0 to 1, and then you see that for intermediate bids you have different allocations. And one of them is strictly higher than the other one. And then once you integrate it out, you will get this result. Okay, so that's if those of you who are teaching auction theory, if you want trick questions for your undergraduate or PhD students, I think that's a good one. Because at first we must have made a mistake, right? Like our first intuition was let's go check the calculator. All right. Okay, so as I said, I mean, this is a very baseline example, right? And the point of this example is kind of 2 points. One is to show that actually things can get restored with this uncertainty over click-through rates, which I think it's important given how massive this industry is. But also that revenues are not necessarily the same as in the second price auction. The difference can be substantial, so they're actually worth thinking about in practical setting. But of course, it doesn't mean that it's always the case, and so we do consider a whole bunch of extensions. So the first one, and this one is really important to understand what's going on, is to have less heterogeneity in click-through rate, right? Because we know that when there is no heterogeneity in click-through rates, when they're both the same, we have the old example with no pure strategy equilibrium. On the other hand, with this full uncertainty, all the possible ratios between the highest and possible click-through rate, like from 0 to infinity, we do have existence. So how can we draw a line between them and connect them? Well, we're saying, let's assume that this Q1 and Q2 are drawn from the uniform distribution from some number U to U plus 1, right? We're just shifting this uniform distribution to the right. And notice that for all of the results, the only thing that matters is the ratio of the higher to the lower. So basically, it's just a way to normalize that. Okay, so now the theorem no longer looks as pretty as before. Instead, what it says is that with probability distributed uniformly on this interval, then existence is going to be guaranteed only for alphas that are less than some cutoff value. Okay, and this cutoff value, and when this cutoff value is satisfied, you have some ugly-looking formula. But one thing to notice is as u goes to infinity, right, the thing that's easy to see is as u goes to infinity, this expression at the top goes to 0. You have u squared at the top, u in the bottom. So indeed, as u gets higher and higher, you get a smaller and smaller ratio of alphas for which equilibrium exists. And here is a picture. That's probably the most informative picture to understand what's going on. So notice that this formula, this candidate equilibrium, just comes from the first order condition. Okay, that we can compute for any alpha and any u. Like that number will exist for any alpha and any u. All right, so you can just inspect it, everything here is positive. And so what we can do is we can say, suppose my opponent is bidding according to this candidate equilibrium, and I'm exploring all the bids from 0 to 1. Okay, which is my value. What is my expected payoff? Right, just as a sanity check, if I bid 1, my payoff is 0 in all of this. Now, let's do it for 4 different distributions. The one on the left, upper left corner, that's the original one I started with, right? All of the scores are distributed from 0 to 1. Second one, we shift them to the right by 0.5. Next one, we shift them by another 0.5. So it's, scores, quality scores. The ratio from the highest to the lowest is 2. And then here, we'll shift it further to the right, so they get much closer, right? So the highest possible quality score is only 1.5 times the lower one. Okay? So what you see here is all of those, right? So this point right here is this candidate equilibrium. Okay? So this local maximum. And what happens is the bigger is the amount of uncertainty, the lower is the expected payoff. Sorry, yeah, that's right. So the more spread is, the lower is the payoff of just bidding 0, just giving up and getting the second floor for free, relative to actually competing in this auction. Okay, and in the base term, still an equilibrium. And here's, you can see that it's still optimal to bid according to this candidate equilibrium. Here it's harder to see when it's still optimal to bid according to this equilibrium. Equilibrium still exists. Once you go here, everything breaks down, right? Because if one of us bids according to this equilibrium, according to this candidate formula, the best response to that is 0. And of course, the best response to 0 is not 0. Okay, so again, we're going to have some more complicated dynamics, but it's not going to be a pure strategy equilibrium. Okay, so bids in this auction will not that way. Okay, I have 5 minutes. Let me tell you just very briefly what else we have. We look at, for the same setting I just showed you, we'll also compare revenues. And it turns out that also becomes more complicated. Turns out that there's also a cutoff above which generalized first price auction gives you more money, and below which generalized second price auction gives you more money. So that can be flipped. And this cutoff is always lower than the cutoff before. I think I got it right. But basically, so this part is definitely right. Right. So if you look at the range of alphas, there is a region where the generalized second price auction has a higher value. There is a region where, yeah, that's correct. But then there is a region where the generalized first price auction has a higher value. And then there is a region where the GFP equilibrium just doesn't exist. Okay, so things can get more complicated. Now, the second extension we have is, this was a very kind of special. Okay, so what happens if you have n slots, n bidders, and general distributions? Okay, so everything else is the same. So then what we show, and it's actually, this is probably the simplest result of the paper. It's not the first one we derived, but once you think of it in those terms, it becomes very simple. The key object of interest here is this function C of R that tells you how many clicks you're going to get in expectation if all of your opponents are bidding 1 and you're bidding R. Okay? And again, what's helpful here, it's multiplicative. If you all double your bids, then the expected number of clicks doesn't change, right? So the only thing that matters is the ratio. And so for something to be in equilibrium, it has to be the case that bidding the same as everyone else is the best response. And so theorem says that this auction, I just described, a very general auction, has at most one equilibrium. Right? We know it cannot exist by the previous example. If it exists at most one, and here's a very straightforward candidate solution, so you can just compute it, right? And then once you know this candidate, then you plot an analogous function, and if this local maximum is also a global one, then it exists, otherwise it's not. So even though we cannot guarantee existence, we have a very kind of straightforward way of checking for any particular setting. And I think one thing I will say, what we also have in the paper, I didn't put it here, not in the paper in my website, but in the paper we're going to upload soon. We have some lemmas, some sufficient conditions. That's the concavity type argument that will guarantee the existence of this equilibrium for various special cases. All right. The last extension that we have, well, more, but what I'm going to talk about is what happens if one advertiser has value 3 and the other one has value 2, right? So they have different values per click. And everything else will go back to the very simplest model. So it turns out that an equilibrium is still guaranteed to exist. Of course, now we know it all depends on this uncertainty, but at least with that amount of uncertainty, you still get an existence. And what we also get, we get really nice comparative statics, some of which are very intuitive and some of them may be less intuitive. So for example, if alpha increases, okay, if the second slot gets more attractive, both bid decrease. Okay, that's intuitive. Now, if the lower value increases, both bids increase, right? So what happens if the lower value increases? That bidder gets stronger, they bid more, and the bidder who is even stronger responds by bidding even more. Where it gets kind of funky is when the value of the higher bidder increases, then they bid more, but the other bidder bid less. Okay, so you have this kind of somewhat unusual comparative effect. Okay, and for revenue, we have some pictures on the paper. It can be anything, right? Depending on the parameters, it's real. So I think for revenues, to say something conclusive, we have a possibility result. The difference can be substantial, but to really know it for sure, you really need to look at your specific setting. Yeah. So these are the pictures for the revenues. I'm not going to go through. It can go any way imaginable. All right. So summary. With this uncertainty that's now prevalent on these platforms, it restores the existence of the generalized first price auction equilibrium, pure strategy equilibrium, if you have enough uncertainty to smooth things out. And it's actually worth paying attention to because revenues may in fact be higher than in the generalized second price auction. All right, thank you, and I think I'm at time, so.
First of all, thank you very much for the okay. I'm going to be closer if I can. Thank you very much for the organizer for the invitation to present this paper, especially Maria Sotomayor that joined this crowd. It was fantastic meeting workshop so far. So this is a joint paper with Ilan Lobel and Omar Mustaki, both of them at NYU Stern. And the paper is about auction, but in a different setting. So suppose that you have to design an auction with ML prediction, machine learning prediction, right? So you have a bunch of buyers, potential buyers, the traditional setting with private valuation, V1, V2, V3, etc. And you have an auctioneer, as always. But now this auctioneer has an access to some signals for each buyer. So the signal is information that the auctioneer can see for this guy from these guys. And the general question here is how to design the auction using such information. So this is a very broad question. What I'm going to do is to address this question in a very specific setting where the intuition here is to really model this ML prediction as I'm trying to motivate. So recently, we've seen that the computer science community has been quite interesting effort in trying to do evolution, this kind of decision making under prediction. The basic idea is that you need to make a decision and you have ML machine to help you out with that. And the ML machine, the ML system prediction could be very helpful in such a setting, but sometimes it could be completely off base. If you use ChatGPT, you know what we're talking about. So sometimes it gets you the right answer for the question, but sometimes it gets you completely off about the prediction. So the question of this paper is there a way to use this ML prediction in this kind of context? In the computer science literature, you've seen that there is some progress in this kind of questions, starting from the very basic problem of binary search. So here's some references that really use this kind of approach to deal with this kind of setting. Specifically in auction and back design in general, we have also growing literature that tries exactly to address this kind of question, but use a different approach that I'm going to be using here. So in this literature, the computer science literature, what they do is kind of using two criteria. One is the consistency, meaning that when you're right, you want to be very close to the truth, but when you're wrong, you want to protect yourself against the mistake that the machine makes, right? Instead of using this worst case assumption or scenario that this literature use, you're gonna keep our understanding in a setting that is kind of be Bayesian approach. Use this ML model sometimes to generate garbage, what you're gonna call hallucination of the machine, right? So in a way, you're gonna use the same kind of idea, but using more standard Bayesian approach to the problem, right? So let me go to the model, unless is there any question about the motivation, what I'm doing here, right? So the model, as you're gonna see, is a very standard basic model by Meyerson. A seller has one good to sell, and there are any potential buyers. Each buyer has a valuation VI drawn from a non-distribution VI with PDF small VI. The seller has a signal, as I was motivating before, SI. That is a signal about each buyer. And the structure, here is the structure of the signal that I'm going to be playing here, right? Which models this idea of hallucination. So the signal is going to be like this. So with some probability 1 minus gamma I, that is probability of a given buyer I, the signal is going to give you the truth, the real value of the buyer, right? With complement probability gamma I, which is the probability of hallucination, this is going to give you some garbage, some value that comes from a distribution that is completely orthogonal to the real distribution of the buyer, right? So in a way, what you're gonna be assuming here, apart from this non-regular case, is that the distributions are going to be regular, have bounded support, have continuous density, and are going to be absolute continuous with respect to each other. So I'm not going to play with that. But as you can see here, there is like a mass point. When the machine gives you the truth, it's going to be as if you're under the direct measure probability, right? So the question is, what is the seller revenue option mechanism in this case, right? So first, before going to answer this question, let me compare the two possible models that we can think of, right? So one is what you call the signal error, which is the common sense when you think about error, is that the signal is going to be some normal distribution with mean the real value and some finite variance, right? So this is the classical way to model signal error, as I was saying. Good model of a signal generated from a linear regression, so you can really use that in a practical way. But the error is going to be local in the way I'm modeling here. So comparison with the hallucination model that I just present to you, the signal here is going to have the truth with some probability 1 minus gamma and some garbage with probability gamma. So that's the way you're thinking of modeling this deep neural network or GPT model, right? So when the prediction is right, the output is wonderful, but when the prediction is wrong, it's going to be completely off base. All right? Is it clear, the model? So in the sense, the error here, the error structure is going to be a global error structure, right? So let's start with the analysis of the model. So the first observation that I'm going to do here, if you really want to try to characterize the optimal mechanisms here, then you're going to end up exactly to the same kind of problem as identified by Kramer-Killing. So there is always a mechanism where the seller is able to extract the full surplus of the buyer, even with one buyer. The idea here is that this structure gives you some correlation between the signal that the seller is seeing and the buyer's reevaluation. With this kind of linkage, so I can really use a mechanism that is going to lead to full extraction. But on the other hand, this is going to be a very non-credible mechanism. So it's use the signal value correlation and applies even for the one buyer case I was saying, but this is deeply non-credible. The mechanism is vulnerable to a deviation to the cell. So meaning that you can really play with mechanisms that are really non-credible. To avoid this kind of problem, you're going to assume the signal is going to be revealed with the choice of mechanisms, saying that the signals are going to be public for the all buyers, right? With that, everyone can perform a Bayesian API data of learning the signal of himself and the other potential participants in the auction, right? So let's compute this posterior belief. So let's denote that delta S as the direct measure function at S. So given a signal S, the seller's update belief is going to be some formula like this. You can derive very easily. That is going to put weight in the distribution of the garbage, right? And the distribution that is the direct measure of the true value, right? For simplicity, for this position here, I'm going to assume that the distribution of the value and the distribution of the hallucination is going to be the same. As I was saying, they are going to be independent, but it's going to be the same. In this case, this gamma tilde that shows up in the formula over there is going to be exactly the gamma that is the probability of hallucination, right? So let's try to use the traditional, right, approach, which is the Meyerson virtual value approach. So if you compute the virtual value, which is exactly the formula over there for this problem here, and given a signal, expose the posterior belief regarding this value is going to be given by exactly this formula over here, and you can apply exactly the same to this distribution. You're going to end up exactly with this virtual value function over here. As you can see, they're going to have some discontinuity over there because you have 1 over gamma when v is less than the signal, and 1 when v is above s, right? So if I show you in a picture, so for the case of uniform distribution between 0 and 1, that's exactly going to be the virtual value for this case. So let's do the following exercise. Suppose the gamma, the probability of hallucination, is 0.1, and the true signal, I'm playing with 1 buyer, just for the illustration here, right? So if you blankly use the Meyerson approach for this case, then it turns out to be that the option price is going to be half, as in the traditional case, right? So that would be the prediction of this model if you use blankly take exactly the price that where the virtual value function is 0, right? But wait, this cannot be right for the following reasons. So suppose gamma is a small number, as it's in this picture here, 0.1, and the true value is going to be something below half minus epsilon, as in the picture over there. So if you compute the revenue of 1/2, it's going to be approximately epsilon in this case, because it's very likely that the half is going to be associated to hallucination. But if you compute, because the hallucination is very small, so it's very likely that the signal that you're seeing is exactly the value. And when you compute the revenue for the price that picks exactly the signal there, that you're extracting all the rent in the scenario that is not a hallucination, then you're going to get exactly half minus epsilon, approximately. So it's meaning that if you use the approach, if you're not correcting for the fact that you have this jump, the Meyerson approach does not apply in this case because you have a mass point. That's the basic observation here, right? But there is an alternative characterization given by my colleague Paulo Monteiro and Benais White that showed up in a paper in Journal of Mathematical Economics some more than 15 years ago that does solve this problem. And what you're going to do essentially here is apply the approach to our problem, right? So their characterization requires a solving an infinite number of infinite programs that I'm not going to do here because my structure here is much simpler than the general case they are dealing in that paper. So what you do in this paper is exactly to develop a machinery necessary for the characterization in order to obtain a structural insights and the explicit solution for this problem here, right? Just to remember us how the iron principle works, let's fix an example, which is the mixed truncate normal distribution. So you take two normal distribution, truncate, and mix them. Then in order to have like this kind of no monotonicity of the virtual value function, what you do exactly the iron principle here in this picture, right? This is the traditional approach by Myers. But in my case, I have the mass point. I cannot use that directly because the mass point, things are not smooth, and I cannot use directly that. The approach that I'm going to use, inspired by the paper Monteiro and Zweiter, is exactly to do a kind of truncate ironing. What is the truncate ironing? I'm going to, for each cutoff, let's say, if I take the whole domain is going to be the irony, which is going to be the convex hull of the integral of the virtual value, which means exactly the fact that I'm taking the monotonic approach for the virtual value. But now I'm going to play exactly with different cutoffs. I'm going to play with, let's say, 0.5, 0.2, and I have different kind of truncate irony. What I mean with truncation is that I'm going to take the problem between 0 and 0.5, between 0 and 0.2 in the value space. Here, I'm taking this picture, projecting the quantile space, right? Where I do the iron principle in the characterization given by Meyerson. So how I use this machinery here, the truncated irony principle, here is the characterization. Here is the main theorem or the general theorem of the paper. So consider Y with values drawn from a regular distribution, meaning that the virtual value is a regular function. For any given gamma and S, signal S, there exists a cutoff T greater than the signal, such that the virtual value is going to be the iron truncate iron between 0 and the signal for values below the signal. And it's going to be a constant, which is going to be exactly evaluated at this capital T, which is this cutoff, evaluated at the virtual value function, the original virtual value function. And for V greater than T, you're going to take exactly the virtual value function that I just showed you before, right? And the optional mechanism is going to be exactly the one given by the seller is going to award the good to the buyer that has this highest correct virtual value, phi bar S gamma I. Okay? So the approach is exactly to correct for the lack of monotonicity given this mass point, and that's the kind of the adaptation of the original characterization by Myers in this case. In terms of pricing, right, let's consider the case of one buyer. So in the case of one buyer, and assuming that F has a log concave, is log concave, right? So the result here is not general as could be, right? But for this class of models, what you can show is that for any signal and any probability of hallucination, there are going to exist, thresholds such that the optimal price is going to be exactly according to this formula. And the interpretation is the following. For signal very low, below this cutoff, the first cutoff at gamma, then as if you're going to ignore the signal. You're going to use exactly the same pricing that you're going to take from the Myers approach. For between two values, L gamma and M gamma, you're going to follow the signal. You're going to believe the signal. So the price is going to be exactly the signal. For price above this M gamma and below, there is a type over there, below U gamma, you're going to have like some kind of cap, right? You're going to protect yourself against hallucination, right? But if the signal is too good, again, you're going to follow again this signal. So it's like, and the formula to exactly characterize where these prices, the ignore price and the cap price are given exactly where the virtual value is going to be 0 for each part of the domain, right, before and after the signal. So here, for the uniform case, here's the picture of the option price, as I was saying. So for low signals, so signals below this first threshold over there, so you're going to use exactly half, as if you're ignoring the signal, between 0.25 to 0.25 and 0.75, I believe. Then you're going to follow exactly the signal. And after that, you're going to have this first cap. For the uniform case, I don't have the second cap. I don't have the second regime. But essentially, the spirit is exactly that. Low signal, you ignore the signal and hope it's a hallucination in this case. Medium signal, you follow exactly the signal. So the price is going to be exactly the signal. And for high signal, you cap, since following a high signal can be, in this case, very risky. But in some cases, you can really want to do that. For instance, for this case here, which is the beta distribution with parameters 1 and 2, and hallucination parameter gamma 0.75, then you see the 4 regimes here, right? We ignore, you follow, then you ignore again, and then you follow again. So these are the 4 charts of the virtual value in this example here. All right? So now the thing is that kind of you solve the problem, but in a way, when you have signals like this, you introduce asymmetry in the game. Every buyer is going to have different signals. It's as if you're facing an asymmetric and complex auction to implement. In this case, on the top of that, with this signal structure that leads to these jumps and this iron procedure that I just showed you, right? So what you're gonna do now, or what you did in the paper, is try to follow an alternative approach to come up with a simpler auction. What you're gonna exactly use is this eager auction that was used before by this paper, Pies and Lemmy. And the eager auction is a family of auctions that have personalized reserve price. How it works? So each buyer gets a reserve price RI and submits a bid BI, right? So this is the only difference from the traditional case is that there is a personalized reserve price for each buyer here. So the rule of the auction works like this. Let's think about the set A of active buyers, which include all buyers that have bid a bid above the reserve price that was designed for this guy, right? So you must allocate, according to the rule of this eager auction, you have to allocate the item to the highest active buyer in this group and charge this guy the max between the reserve price of all guys and the highest active bidder of the other buyers that is not the winner, right? It's as if you're in the second price auction, or you take the highest possible reserve price among these guys that are active in the auction, right? So with this auction, which is used in practice, this literature here, this paper by Pies and Lemmy is from a computer scientist that studied this kind of auctions. What you're gonna try to do is to adapt, right, our formula that I just derived to you using this kind of structure, eager price auctions, right? So one natural idea is to use the reserve price as the signal process. So what you're gonna call the signal eager auction, right? Observe that this is gonna be optional if there is no hallucination, because this is gonna be exactly in a world where you're gonna see exactly the real signal is going to be exactly the value, and this is going to give you exactly the maximum revenue possible in this case. The other possibility is to use the second price auction with the monopoly reserve price, which is exactly the reserve price that you pick from the optional auction by Milestone, which is again the optional case if you are in the world where you have complete hallucination. So in these two streams, these two auctions are going to give you the best possible auction. What you want to understand what happens in the middle when the hallucination is between 0 and 1, right? So we can think about some kind of hybrid kind of auction that use the beta of the signal eager and the second price auction with this monopoly reserve price. Okay, this could be a possible approach for the problem. I'm going to show you in a minute the pictures that compares this mechanism. Another idea relying on our one buyer optimal case is to use the reserve price coming from the one buyer theorem as the reserve price. What I'm going to call the signal buyer eager reserve price, right? The formula that I showed you for the one buyer case. Perhaps the single buyer eager beats the hybrid because the hybrid is going to combine the best two features in the stream case, right? Here are the pictures, right? And this is, I'm doing for, there are other examples in the paper, numerical example in the paper. I'm just picking this one here, which corresponds to the beta 5.1 case. As you can see, the signal eager, here you are seeing the ratio between the signal eager revenue compared to the optional revenue, the one that I can pick from applying the optional auction that I characterized in the theorem I showed you, right? So when you see the comparison, when the hallucination is too big, the performance of the signal eager is going to be very poor, right? Because this is exactly when you have the whole hallucination, and the best you can do in this case is to use exactly this the second price auction, right, for very extreme values of gamma. And the hybrid is going to be something between, but as you can see, there is a region over there in the middle where the single buyer eager is suboptimal compared to the signal eager option. And the thing is that the single buyer eager has this kind of cap in the form I showed you. And the cap is to protect you against the very extreme hallucination case. If you take this out, and that's exactly our final idea, if you take, let's say this theorem was proved for just two bias, what you show formally is that the expected revenue from partially uncapped eager, that is exactly taking this one bias eager without the cap part of the formula, is greater than the revenue from the signal eager design. And again, in a picture now with this logo normal distribution for the value, you see for two bias exactly what this theorem is saying, right? So you see the comparison between the signal eager to the optional, the hybrid, and the partially uncapped eager to the optional revenue. And you see the performance of this design of the partially uncapped eager is pretty good, right? How much time do I have? Who is controlling my time? I don't know. Huh? 10 minutes, right? Yeah, I have more than I need. So here are the main takeaways of the model I just showed you. So basic model of ML prediction inspired by this algorithm with advice. What I have here is that wrong at random as opposite the adversarially wrong as in the tradition of the computer science literature. The main technical contribution is exactly the characterization of optimal auction in this kind of setting where we have the hallucination as a model. And for the single bias case, the optimal policy is often is ignore for low signal, follow the medium signal case, and cap for a very high signal, right? For the two bias, the proposed partially uncapped eager's auction beats the signal eager as our proposal to use this in practice, right? In this kind of model. In the paper, we have some other extensions. One extension that you can think of is the model I showed you is very extreme. Let me go back to the model. In the sense that when the signal gives you the truth, is the precise truth. You can really extend the model, and you did this in the paper. I'm not showing you today here, but you can really play with this local error term there. You can put a v plus epsilon, which epsilon is this local error. This is not necessarily that the model has exactly this feature, but it's true that if you play with this case, which is a very extreme case, it gives us this nice formula of the characterization of the one bias case that lead us to the type of proposal of the eager auction I was showing you before. So just saying that we are doing some extensions regarding to this extension of local error plus the global error that correspond to the hallucination model. Plus, we are trying really to prove more formally that the proposal eager auction that we are doing here is performs well, not only numerically, but in terms of estimation between the difference between the option value and the revenue that you can get from this eager auction. I think that's all that I have to say. Is there any question? Yeah.
I'm aware, I think, oh. I'm aware, I think, of results of Bulow and Klemperer that compare optimal auctions to more simple auctions with with more bidders. And the result, I think, is that if you add a bidder, you can compensate for not having an optimal auction. Correcting for the mistake I've made in characterizing the result, do you know if something equivalent might be true or comparable with his?
Well, in a way, you're trying to see this kind of result, right? Because you know that the optimal auction is even in the minus case when you have a symmetry. It's not easy to come up with a implementation kind of result. Now, what we're trying to propose here
There are options, a way to approach the revenue that you can get, the best revenue you can get, with a simpler kind of structure. I think this field should be.
Yeah, the issue is whether you can quantify a trade-off between the number of bidders and the complexity of the auction.
Here you're not playing with the number of bidders, but can be an idea also to see performance increase the number of.
Thank you.
Any other question for me? Well, the other speaker, I think, left already, no? Oh, it's there. You can ask to him as well. If not, let's close the session. Thank you.
Achei legal. Quando você tem, você usa aquele sinal, quando você tem aquele threshold para os limites, né? Que você aceita. Mas qual a razão de você ter colocado meio, quando o sinal for menor do que aquele threshold de low?
O threshold ali é o sinal, na verdade, né?
Ah, tá.
O threshold é que determina, na verdade, as regiões onde você vai fazer o wiring procedure.
Sim,
você tem mass point, você tem uma falta de monotonicidade, você tem que corrigir, tem que fazer uma espécie de wiring. Então, o que eu estava mostrando para você.
Esse é o wiring.
Esse é o wiring.
Tá.
Mas é um wiring truncado porque você tem antes e depois do sinal.
Geralmente é só no ponto.
Em geral, quando você tem perda de monotonicidade, como a figura que eu mostrei, mas aqui o mass point introduz uma falta de monotonicidade que não dá para tratar exatamente como o Myerson tratou, é diferente.
Tá.
Você tem que fazer um outro tipo de iron procedure, que eu não entrei nos detalhes aqui, porque é técnico demais.